Stop guessing which embedding model works best and learn how to scientifically benchmark them on your own specific data. This beginner-friendly course walks you through every step of the pipeline, from extracting complex PDF text with vision language models to generating synthetic test data with LLMs. Emad Sadiq will teach you essential tools like llama.cpp for local execution and ranx for calculating professional metrics and statistical significance. By the end, you will have the skills to visualize vector clusters and confidently choose the right model for your application.
Hi everyone and welcome to this course. Here I will teach you how to benchmark embedding models on your own data. This course is beginner friendly because I teach everything step by step. Even if you know nothing about embedding models or how to benchmark them, you will still benefit from it. This course is divided into multiple stages, and each stage is divided into theory and practice. I do it this way so that you can understand exactly what the code is doing. In this course, you are going to use both closed source and open source models. If you have the hardware, you can run models locally, but if you don't, no problem. You will still be able to use APIs to access these models. And the cool thing about this is that embedded models are cheap. And you'll see in the course that, in my case, they cost me nothing. By the end of the course, you will be able to generate a table that looks like this, where you will be able to compare a lot of models. And in my case, I used a lot of open source models and two models that are closed from Google and OpenAI. And you'll see that you'll be able to use multiple metrics to compare these models. And I will also show you how to use statistical testing to aid you in analyzing the results you get from the benchmark, because sometimes models might get lucky and that'll help them get higher scores. But with statistical testing, you will be able to compare the difference and see if that is significant or not. You are going to learn the difference between multilingual embedding models and models trained on one or two languages. This is why we need to translate the datasets, let's say from English to Arabic or other languages. And to test this correctly, you will take the text and embed it, reduce the dimensions to do this, but we can plot the dataset in a 2D plot. And the goal here is that multilingual embedded models should reason across concepts instead of languages. So to test this, we are going to take a question, let's say in English, and translate it to Arabic. And in the plots, we should see that a multilingual model will put them in the same spot. But if we use a weak model that was trained on one language, we will see that those two data points are going to be far apart, which means that this model has not that capability of reasoning across concepts. We will see that in the benchmark that this affects the results. So for weak models, the performance will drop to 0 when we ask questions in Arabic while the text chunks are in English. But with multilingual models, the performance is not going to drop a lot. If we take the initial case where the questions are in English and the text chunks are in English, we will get a score. And in the second case where we change the languages, where we have questions in Arabic and the text chunk in English, we will see that the performance will be closer to the initial benchmark. And these benchmarks, we are going to perform them in the first step manually, because I want to teach you the formulas behind the metrics. But after that, we will move to a cool Python library called ranx that will make it easier for you to pick metrics just by calling them and using statistical tests. As you can see, we have a lot in this course, but trust me, you'll enjoy it. If you have any question, feel free to connect with me on LinkedIn or just send me an email. You will find my information in the video description. And don't worry, I'll answer everyone. I've also open sourced the slides, the source code is on GitHub, and the dataset is hosted on Hugging Face. I'll make sure to leave the links in the video description. And I have another note before ending the introduction. Please watch this course at your own pace and don't just watch it. I have provided everything for you so that you can open your IDE, clone the repository, download the dataset, and run the notebooks alongside me. This way, you will learn effectively from the course, and feel free to change the notebooks, break them, use your own datasets, because if you don't do that, you will not get a lot from the course, but by trying multiple things, you will learn from it a lot. That's all I have to say for you. I wish you the best. Good luck and enjoy the course.
Hi everyone! In this course, you will learn about how to benchmark embedding models on your private data. It is quite challenging to choose a model because there are so many of them, and some companies prefer to either use small open source models that they can run locally or proprietary models. You should also take into consideration the cost of using an embedding model and the resources required to run it. Let me show you a brief introduction on what we are going to do in this course. Embedding models are used to convert text, images, or audio into a dense vector. In this course, we are going to focus on the text modality. If I take this sentence and give it to an embedding model, I will get a dense vector with a fixed size. The size of the vector is not the same across every model. Some will output a dense vector of size 512 and others will go up to 4096. I'm going to show you where to find this information in the next slides. Why do we use embedding models? We use them to build systems like retrieval augmented generation and recommendation systems. The dense vectors that we get from the embedding model capture the meaning of the text. This allows us to build amazing search products. The big question is, how do we choose an embedding model? Because if you do some research, you'll find that you have models from Google, OpenAI, Qwen, and other model creators. Some models are free and open source, while others are proprietary. The answer to this question is benchmarks. There is a leaderboard called MTab that ranks every embedding model based on their performance on a lot of benchmarks. Let's check it out. Click on this link to open the leaderboard on Hugging Face. On the left navigation drawer, you can see that we can choose if we want to care about models that are multilingual, or here they selected English, but we can select a specific language. By default, multilingual is selected, but you can expand the language specific section to select a language you are interested in. We don't have a lot of languages, but at least we have something to select. If you select French, for example, you will see that the table will be regenerated. We have also an option to select domain-specific benchmarks like coding and others. And if you are interested in other modalities, expand the image section and choose what you want to explore. Even though MTab started as a benchmark or as a space to rank embedding models that transform only the text, now they support also image embedding models, and this is something that will help you choose a model. Now let me close the navigation drawer, and we have another option to customize the table, and that is done by expanding the customize this benchmark section. As you can see, we have a lot of stuff. By default, we have 1038 languages, 131 tasks, 9 task types, and 20 domains. In my case, I am interested in only retrieval task types, so I will keep just retrieval, instruction retrieval, and STS. Let me do that quickly. There you go. Here are the tasks that I am interested in. Here are the domains. Let's keep all of them. The modality is text. Here we have the 1038 languages. Let's also keep them. And yeah, let's also keep every single task. Now expand the advanced model filters. You will notice that we have the option to select only open source models or only proprietary models, or by default, we have both of them. Here we have the size of the model. By default, they selected greater than 10 billion. But if you are interested in running small models, make sure to click on one of these options. But in my case, I'll keep everything as default. And now let's look at the table. Here we have different tabs. The first one is summary. It shows us the performance of each model on the different tasks that we selected. You can see that here we have retrieval, STS, and instruction retrieval, which are the 3 tasks that I have selected here. The zero-shot column refers to the model's ability to perform a task without any specific training on it, because you can increase the performance of the model just by fine-tuning it on that specific task. But we don't want to do that. We want to see if a model generalizes to different tasks that were not present in the training set. Next, we have the memory column, but it's not appearing. I think I need to decrease the size. Yes, I decreased the size of the page and now I can see it. So this is showing the memory usage in megabytes. And this size is the size required to run the model in full precision. But we will see this in the course. If you don't have, let's say, 28 gigabytes of VRAM, we can do a trick where we quantize the model to reduce the size by a factor of, let's say, 3 or 4. So instead of 28, you will need only 7 gigabytes of VRAM or even less. We will see how to do this in the course. We also have the embedding dimension. This is what I mentioned in the slides. For example, here with the latest Qwen3 embedding model, we can go up to 4096, but other old models may have very small dimension size. And finally, we have the maximum tokens. This is the maximum amount of text that the model can accept. This is in terms of tokens, so you should convert this into text, but 32,000 is a lot. It's a lot of text. And finally, here in these columns, we get the scores on each task. In this case, with the tasks that I selected, the Qwen3 model is beating the other models on every task. If you look at SCS, this is the highest value, the same for retrieval, and the same for the mean. But here, the only task where this model did not perform the best is in this one, instruction retrieval. But if you compare it with the other models, the score is very high. For instance, this Gemini embedding model has just 5.18. Qwen has 10.06, which is really high. Okay, so there are other tabs that you can select. For example, the performance per model size. This is a graph that shows you the accuracy. So here we have the mean of all tasks in relation to the number of parameters. You can see that bigger models tend to give us the highest performance. And if we look at here, you can see that we find the Qwen3 embedding model. And there are other tabs. I'm not going to go in details, but if you want, you can come to this space and check it out. Now you know how to navigate this space. Let's go back to the slides. Now we have an important question. Should we trust these public benchmarks? I'm not sure if you are familiar, but with large language models, every time a new model is dropped, we see that the performance on benchmarks increases dramatically in some cases. And people are skeptical of that performance. Here, in this case, with embedded models, it's a different story. Because we have a lot of benchmarks and all those benchmarks are tailored to specific tasks, if you decide to train a model on, let's say, a number of tasks to be very well, you will find that this model will perform poorly on other unseen tasks, and this will show on the table. So in my case, I selected only 3 tasks, but let's imagine if I have selected 10 or 20, that model will not appear on the top of the leaderboard. So which means that the answer to this question is yes, but if you are still not convinced, you can create your own benchmark. This is exactly what I did at the company where I work currently. I used our private documents to create a dataset that is clean, diverse, and multilingual. After that, I selected a few models that we could use and I benchmarked them against this dataset. And the good thing is that I got the same ranking positions. So in my case, Gemini was beating, I selected 3 models, Gemini and the OpenAI models. And on my dataset, I saw that Gemini was performing better than the OpenAI models. And this is the same thing that we have here. You can see that we have Gemini, but the OpenAI models do not even appear in the top 10 leaderboard. So after creating that benchmark for my company, I wanted to share this technique with you so that you can also perform this if you want, either on your own data or for the company that you work for. In this course, you will learn how to create a golden dataset. I'm going to define this term in the upcoming tutorials. You will also run open source models locally and proprietary models. I will show you how to compute metrics to grade the models. There is a library that we are going to use and that performs statistical tests, which is a really awesome feature. Statistical tests are going to be used to prove if a model is better than another. I'm going to explain this later. After that, we are going to automate some steps in the pipeline. I am not going to automate the whole pipeline because there are some steps where we need to ensure that the quality of the data is very high. And finally, I am going to show you how to generate the tables to compare the models. And this is what I was talking about. These are the 3 models that I compared using the private dataset. And you can see that Gemini is beating the OpenAI models. We are going to do the same thing, but I'm also going to include other well-known open source embedding models. You will learn a lot of stuff in this course. And don't worry if you are a beginner. I will go step by step to make sure that everyone benefits from this course. In this video, I will show you how to extract text from PDF files. I won't cover the other document types because extracting text from them is straightforward. Extracting text from PDFs can be challenging because they might be scanned, have complex layouts, or contain text in different orientations. We also need to deal with images, tables, and other elements that can be present in these types of documents. In Python, there are many libraries that can extract text from PDFs, such as PyMuPDF, PyPDF, and PDF Plumber. Let's take this page that I took from a PDF file. If we give it to one of these libraries, the output will contain the selectable text on the page. Let me zoom in on this small text in order to verify the result. Notice that Quantum Black AI by McKinsey does not appear in the output. That's because this text is not selectable. The rest was extracted by PyMuPDF, but the order is wrong. For example, if we look at March 2025, here it appears in the end of this page, but in the output it appears after the title, which is wrong. And also let's look at the subtitle. Here it appears directly after the title, but here in the output it appears at the end of the text, which is not correct. These Python libraries are ineffective because they don't preserve the document's structure. We will see some complex examples in the next slides that show the limitations of these tools. So, if we shouldn't use these libraries to parse PDF documents, what should we use instead? The answer is vision language models. VL models can see images, read and understand text, and combine both abilities to parse an image effectively. This time the output is perfect. The structure is preserved, and the model even extracted the non-selectable text. Also, notice how it added the new line character to match the style of the original page. So instead of having Quantum Black AI by McKinsey in one sentence, the model understood that there is a new line character that should be added. And the rest is also good. So you see here we have the title next to the subtitle, we have a new line, and here we have the authors, and finally we have the date, which is March 2025. You might be asking, what is the trade-off? Let's compare both methods side by side. Python libraries are free and open source. VL models can also be free, but we also have paid options. Libraries can't handle scanned documents, while models can. When it comes to resources, you don't need a powerful laptop to use the libraries, but that's not the case with VL models. Here you can see that I have two values, high and low. If you decide to run the models locally on your laptop, you need decent hardware. You need to have a GPU in order to get fast responses. Here, low means that instead of running the models locally, you will connect to an API and use the model that is hosted on the cloud. VL models have a clear advantage because they preserve the structure of the document, they handle complex layouts, and understand the content of each page. However, models are slower than traditional libraries. Overall, VL models perform better, but it depends on your use case. If you are working with simple documents, use Python libraries. If you have thousands of documents with different layouts or need to extract specific information, go with VL models. As I said, we will compare both these methods in complex examples. This is an image that I took from the same documents that I mentioned in the beginning. And you can see that here we have a lot of stuff. And in the middle, we have this chart, which contains 6 vertical stacked bar charts. And we have a lot of tags. So let's test both methods to see which one will perform best. Here is the output from PyMu-PDF. Look at the numbers inside the chart. You can see that here we have 50, 57, 46, 36, and we see them here in the output. The problem is that each number is placed on a separate line. The words McKinsey and company don't appear in this image, which means that this text is extracted from another section. This text that I highlighted shouldn't appear at the beginning of the output, because as you can see, it appears below the chart, which means that PyMu-PDF should have extracted this after the main content. And finally, you can see that it swapped the title, and the title now is appearing after this. The title should be at the top. Here is the continuation because I couldn't show the full output in one page. You can see that here we have another problem. Here, if you look at the image on the right, we have the legend. So each color means something. For example, the light blue color means fully distributed, this gray color means hybrid, and this dark blue color means fully centralized. We can see that output here. You can see we have fully centralized, hybrid, and the other one should be below. But the problem is that instead of getting just one sentence, PyMu-PDF decided to split the output across multiple lines. This is not a problem because this is how it appears visually. But it will be better if we could get them in a single sentence so we don't have to remove all those new line characters. That will save us a lot of time. Now let's look at the output from the vision language model. Here I decided to use Gemini 2.5 Pro. The result looks much more organized. The title appears at the beginning, like we see in the image. The model also gave a description of the image because I asked for it in the input prompt. This is something really great about these models, is that you can describe what you want. Pause the video and read the description if you would like. I have highlighted some terms that appear in the charts to show that the model actually understands what it is seeing. For example, here we have centralized hub model, we see it here. We have decentralized spoke model. We have fully centralized, hybrid, and fully distributed. That comes from the legend, etc. And instead of listing the numbers inside the vertical bars, line by line, the model produced meaningful explanation. You can see that let's take risk and compliance as an example. Here it gave us 57% fully centralized, 30% hybrid, and 13% fully distributed. Let's look at a second example. As you can see, it is complex. It contains a lot of graphs. And again, I took it from the same report. Let's start with PyMu-PDF. Unfortunately, PyMu-PDF still doesn't give us a good output. It repeats the same mistakes. You can see that the numbers are, again, split by line, which is not ideal. Let's look at Gemini 2.5 Pro again. Let me say one more time, the output from the model is excellent. Try reading it, you will be impressed. The model correctly identified that there are 14 charts, as you can see. Here is the description of the image that Gemini 2.5 Pro gave us. It says that the image is composed of a series of 14 area charts, and it knows that we have 2 rows and 7 columns. This is why I told you in the beginning that these models can see and read and understand text, which is really awesome. It also was able to read the values in the x-axis and in the y-axis. So here it says between 0 and 50. One thing I noticed is that in this case, the model started to guess some of the values. I actually think that this is interesting because the guesses weren't bad. Let's look at the inaccuracy line plot. The model estimated that the values should be 32% and 45%. If we look at the first points, you can see that it is higher than 30 and it is close to 32%. That's good. And here the other point is higher, is between 40 and 50. That's why I said that the guesses were not bad. I am mentioning this so you are aware that models can sometimes add information that isn't there. It is always good to double check the output. In this course, we will verify everything manually because we want a high quality dataset. That's fine, since we will only need a few hundred samples, not hundreds of thousands. But even with that, the model saves us a lot of time. Without these models, we would waste countless hours cleaning the messy outputs that we get from as you saw from PyMu-PDF or the other Python libraries. VL models will help us create high quality datasets by annotating images. We don't want to remove this from the dataset. The models can describe tables because, again, tables are full of values, but if we just store those, they don't mean anything. We need to have context. So with these models, we can describe the content of these tables and also output them in a nice format like Markdown. We can preserve the layout. We can extract only what we need from the documents. So for example, if you want to extract, let's say, just the titles or some keywords or something from the documents, you can write a prompt that will instruct the model to look just for those values and ignore everything else. The most important thing is that these models can handle scanned documents. If you try to use PyMu-PDF, the output will be an empty string. There are other OCR solutions, but they don't perform as well as the vision language models. So which model should you choose? You have two options: proprietary models or open models. You can use both through APIs. It is cheaper than hosting your own GPU server, but if you already have the hardware, you can host open-weight models locally. Just keep in mind that this is expensive. Finally, I want to share two leaderboards you can use to track the best models. We have OpenVLM and the Intelligent Document Processing leaderboard. That is it for the theory. Now let's move on to practice. The source code is available in this GitHub repository. You'll find the link in the video description. I have opened the project in VS Code, and here I want to show you the notebook that you need to open. Open the notebooks folder and choose basically the first notebook. Inside the data folder, you'll find the documents that I will be using in this course, and also some images that we will use for testing. If you click on this one, you can see that this is the image that I showed you in the slides. Now let's go back to the notebook. First, we will start by using the Python libraries. And also, before I forget, you will find the requirements inside the requirements.txt file. Here are all the dependencies that we will need. Here I am using PyMuPDF, but feel free to use the other ones if you want. Let me show you the documents that I will be using in this notebook. It's called the State of AI. So this is the document. It contains 26 pages. Let me go back to the notebook and let's start by running the first cell. You can see that PyMuPDF correctly identified that we have 26 pages. That's good. And in order to extract the text, you can loop over the document. This will allow you to loop over the pages. And from each page object, we can call the getText method. This method will go through the page, extract the selectable text that it finds there. And if I run this, you can see that I get this thing. So it says that extracted 50,000 characters of text. I am doing this just to make sure that we get something, because we'll see later if we have a scanned document, we should get an empty string, which will return 0 characters. Let us print the first 2,000 characters just to see how the output looks like. As you can see, we have a lot of new line characters. This is exactly what we saw in the slides. So again, here is the first test that I have conducted with this method. This diagram or this figure appears in the 5th page here because this is 0 indexed. We select 4. If I try to get this text, and you can see that we get a lot of output from it because we have other stuff other than the figure. But let me put it here on the side and let's look at it. You can see that here we have exhibit 1, that's correct. And here are the numbers that are inside the bar chart, but this is not ideal. And again, we have a lot of new line characters. When you are done, make sure to close the documents if you no longer need it. So let's do that. And now let's load a scanned PDF. So basically I took a PDF and I converted it into images. The PDF is this one. As you can see, I converted it into an image. As you can see, I cannot select anything, and I made sure to decrease the quality of the image just to test the performance of the vision language models. So let me close this document and let's try to use PyMuPDF to basically read text from it. First of all, we just check the number of pages. This is correct. We have 19 pages. After that, we use the same thing, but this time we get 0 characters because this is a scanned PDF. So this is the problem. If you have a lot of scanned documents, you can't use these Python libraries. But luckily we have multimodal models or vision language models. Multimodal means many modalities. A modality can be text, audio, video, images, and here these models can understand 2 things, images and text. This is why we call them multimodal models. Here I will start with proprietary models. I will use Gemini, but feel free to use OpenAI's models or Grok or any other proprietary model. I use Gemini because I really love that 1 million context window, and it is currently the best model at document understanding tasks. If we look at the leaderboard that I mentioned in the slides, the intelligent documents processing leaderboard, you will see that Gemini is basically the best. So this is why I am using it in this notebook. With Gemini, you need to do some things in order to be able to access the models. First, go to Google AI Studio and make sure to create an API key. Click on this button and give the API key a name. Choose a project. If you don't have a project, you can create a new one. And after that, you can click on the key, copy it, and paste it in the .env file. Now, when I use the .env package in Python, it will load that API key. And if you are wondering what you should put in the .env file, basically you need to have this thing. So the key should be called Google API key. And here you paste the key that you created in Google AI Studio. After you do that, load the keys. And here, as I said in the slides, we can instruct these models to do a specific task. For example, here, if you read the system prompt, you will see that I told the model that we will give them a PDF document, and the goal is to extract the entire text. I mentioned that the document can be simple, complex, or even scanned, just to let the model know that the variations of the documents that he might encounter. I've also made sure to explain that the model should examine the documents page by page, because here you have two options. You can either pass one image at a time or one page at a time, or give them the full PDF document to the model. And the model will try to understand or will try to analyze the document page by page. And here I said that when you come across text, extract it as is. I don't want the model to add anything else. And also I have made sure to tell the model that if it sees images, to give us detailed description, because this is very important. We don't want to skip images. Also, we have something we tell it if it encounters tables to describe them also like images, etc. And finally, we say here is the PDF, and after that we will provide the PDF document. After that, here is how we use the Google Generative AI package. It's really easy. You can see that here we specify the document path. Here is the prompt. Basically, this is going to be the user prompt. This one is the system prompt. And here is how we use this. Here I am using Gemini Flash, but for you can also use Pro. I use the Gemini 2.5 Pro because it is very good, especially if you have big documents. Gemini Flash is good if you don't have complex documents, and it is faster than Pro. But here, just for testing, I am using Gemini 2.5 Flash. And also keep in mind that with the free tier, you have access to both Flash and Pro. Here in the rate limits page, you can see that we have requests per minute, tokens per minute, and requests per day. And here are the tiers. Basically, when you create an API key, by default, it's going to be in the free tier, but you can upgrade it to tier 1, 2, or 3. And here are the models. So for Gemini 2.5 Pro, in the free tier, you get 5 requests per minute. That's really great because processing one document will take 1 or 2 minutes, especially if that document contains dozens of pages. And for Flash, we get 10 requests per minute. This is very generous, and I really like this, especially if you want to test the model before going to tier 1 or the other tiers. And if you jump to tier 1, you get 150 requests per minute. Something to keep in mind. So this is another page that I will link in the video description. It talks about API pricing. Here in Gemini 2.5 Pro or the other ones, this is similar. Here, if you use the free tier, the documents or all your conversations will be used to improve Google's products. But if you go to the paid tier, they will not use your data to train the models. So if you are using the company's data and you don't want Google to use those documents to train their products, then make sure to use the paid tier, or if your company is using Vertex AI, that one is secured and they will not use your data. But for the free version, if you want to try it on documents that you can use, that are publicly available, just to understand if this model will be good enough or not. Same thing for Flash. You can see that here for the free tier, they will use your conversations to improve their products. Otherwise, for the paid tier, they won't use this. So this is something that you should keep in mind. Now let's go back to the notebook. And here I am using Gemini 2.5 Flash. I provide the prompt. I pass the whole PDF document. This is really great. So instead of having a for loop looping over the pages, we just give the PDF to the model. And after that, we add the user prompts. Okay, so the user prompt says, extract the text from the PDF, please. And the model, based on the system prompts, will know what to do. Also keep in mind that there is a limitation. If you decide to upload PDF files, they should not be longer or larger than 20 megabytes in size. If this is the case, make sure to compress the documents or separate them. So if, let's say that the document contains 500 pages, you can separate it into PDF files that contain just 100 documents or less. It depends on the size of the document. Or you can use the File API. The File API allows you to upload the document in Google's servers. This way you can upload bigger files and use them in your prompts. And after that, they will be automatically deleted after 48 hours, if I remember correctly. You can check that information by clicking on this link. And as you can see, they mentioned that the File API allows you to store 50 megabytes of PDF files, and they are going to be stored for 48 hours. After that, they will be deleted. I'm also controlling the output. This is important because if you have bigger documents, you need to allow the model to generate a lot of tokens. I think the max output tokens is 64,000 tokens or something like that. But here, since this document is not that big, 32,000 is very enough. Okay, so now we can run this and let's wait. After that, in the response, we can access the text attribute and get the output. Instead of waiting, let's just open the document and let's compare the result. Let me put the document right there and VS Code on the left side. Let me also click on text editor and let's look at the output. So first, you can see that here we have Rockstrix that appears here, Gaming Notebook PC, and after that, it went straight to the second page. So we did not extract this information. And after that, it says copyright information, etc., no part. And then we have the table of contents that appears here. Let me decrease the font size so that we can see everything. Let's see. So the last one is 109. As you can see, it says simplified UKCA declaration of conformity. That's right there. Okay, so it seems to be working. Let me go to the last page. Here we have something about color. So you can see that, for example, here we have a table and it converted it into a markdown format. You have color, status, solid white, solid orange, blinking orange, lights off. After that, it also extracted these things and the notes. So it seems to be working. Sometimes if you get something that is missing, if you want to add these terms, you can just edit the output. So the request has finished. It took 43 seconds with Gemini 2.5 Flash. And as I said, we can get the text from the text attribute. And now I got another response. Okay, so this time the model was able to extract this. So high definition multimedia interface, that's correct. Revised edition V5, December 2024. And here it tried also to describe the image. So here it says a dark metallic background with a prominent style, etc. So it is trying to describe the Asus ROG logo. So if we don't need this, we can just delete it afterward. Okay, now let me close this document because I no longer need it. And after that, let's save this output. It's better to save the output so that we can open it like this and start editing the output as we like. We will see this in the upcoming tutorials, but for now, I just want to show you how we extract text with vision language models. So that was Gemini. As I said, if you want to use other models, feel free to do that. But this is the go-to model that I use when I want to extract data from PDF documents. So now let's close this with proprietary models section, and let's go to open source models. We also have very good open source models that can do the same thing. And here I will start with the Granite Docklin 258 million parameter model that IBM has released. And I'll show you two ways of using it. We have the transformers library, and here you can see that we have this class, auto model for image text to text. And here we specify the model, and here we are using PyTorch, and it will automatically detect if you have a GPU or a CPU. If we run this, for the first time, this code will download the model from Hugging Face, but later it will just load it from the cache. So that will be faster. In my case, I have already downloaded it. That's why it's not going to take a lot of time. And here, if I try to print device, you will see that it will give me CUDA because I do have a GPU. But if you don't have it, the code will fall back to use a CPU. Having a GPU will definitely help get results quickly, because you will see that here we have a problem with the transformers implementation. So first of all, we load an image because this model expects images. And here we create the messages list. Here we have two roles. We have the user role, we have the user role, but we specify two things. We specify the image and the prompt. So the prompt is convert this page to docklink. This model, you can see that it is very small. It has 258 million parameters. That's not big. But the trick is that this model was trained specifically to extract text in a structured way from PDF documents. This is why it is very performant, even though the size is not that big. So here in the messages list, we provide the prompt and the image because this is what the model expects, and this will give us the list of inputs. If we print the inputs, you will see that this is, let's look at it. Okay, you can see that this is just a tensor. So we have the pixel values that comes from the image. And we also have, so I had to do some transformations in order to get that value, but we have the pixel values and the input IDs. The input IDs come directly from the prompt. After that, you just run this. So you specify the number of tokens that you want to generate. This depends on the amount of text that is present in the image. You call the generate method and you wait. After that, you get something that they call document tags. So let me run this because it is going to take 5 minutes to process. Even though this is just an image and I am using a GPU, for some reason it takes a lot of time to process this. And this is a bug that everyone seems to have, but luckily there is a solution to this. We will see it later in the upcoming cells. And as you can see, these are the tags. Basically, as I told you, this model was trained specifically on this task. And the model, when it finds something, it tries to give you a bounding box. So for example, this text, let me show you the image that I am using. So test OCR is the image that we are testing. And if we look closely, you can see that here is the title, energy budget of something, etc. Here it is. So this is the title. And here the model is giving us the bounding box. And here it's also telling us that this is the page header. So these are tags that keeps the semantic, which is really cool. And after that, we also have, let's see, we have other stuff like formulas. Here you can see we have text, we have section header level 1, etc. So we have these tags that this Docklin model works with in order to extract the text from images with high accuracy. So as I told you, this is going to take 5 minutes, but instead of waiting, I'll just walk you through the notebook. Let's see the next step. You can see that here we are calling the from doc tags and image pairs. Basically, we'll provide that output that we got before and the image. This will clean the text. It will just give us the text inside those tags. And we can export it as Markdown. And we use the display method to display that Markdown. I'm not sure if you are hearing my GPU, but you can see that here the temperature has risen because the model is running. So I hope that you don't hear that noise, but let's keep going. I will bring the image again. Let's put it on the right side and let's look at the output. So you can see that because the output is in Markdown, we can render the formulas. As you can see that the model is doing a great job. And this is a complex document. The layout is not, try to give this PDF document to PyMu PDF. You will not get something like this. It's going to be extremely difficult to clean the output from the Python libraries. This is why it is really cool to have these vision language models that understand the complexity of the layout and give you the text in a clean format. Even though they will never be 100% correct, but at least if you want to modify the output, it's going to be easier for you to do that. Let me go back to the previous cell just to see where it is. As I told you, this code will take 5 minutes before giving us the output. Let's print this, and as you can see, I get the same output. Let's keep going, and let's run this just to make sure that it's working. And yes, it is. Again, save the output to a text file so that you can modify it later. I told you that even though this is a problem, luckily there is a solution. We can use a project called llama.cpp. If you are not familiar with llama.cpp, it is a project that was created in order to make it easier for everyone to run models locally. And it is efficient and it allows you to run models on CPU and GPU very efficiently. And the project, you can find it on GitHub. Here it is. The people who are working on it, they try to support all the models that are on Hugging Face. And to set up llama.cpp, you can read the README file. They have all the steps that you need to follow in order to install it locally. Or if you want, you can read my article. I have created an article where I explained how to install llama.cpp, llama.swap, etc. locally. If you are interested, make sure to read this article. I'll make sure to link it in the video description. So now let's go back. And llama.cpp works like this. Basically, you need to download a model. Click on this link. It will take you to the ggml.org repository. Here they have added the Granite docklink model. So how this works? Basically, you need to download the model in this format, GGUF. If you look at the model that was uploaded by IBM and click on Files and Versions, you can see that this model comes in the safe tensors format, and llama.cpp does not understand this format. You have to convert it. Luckily, people in the community convert these models for us into this format that llama.cpp understands, which is called GGUF. And the cool thing about this is that you will have just one file. But with safe tensors, especially if the models are big, they are going to be split into multiple safe tensors files. Make sure to download one of these models. And here you will see that here we have one with Q8 and this one is F16. So Q8 is a version that is quantized. You can see that the size is basically half of the F16 model. And here the F16 model will have high precision and this one will have half of that precision. And after that we have the mmproj. Why do we have two files? Because here llama.cpp will divide the model into two parts. This mmproj will contain the vision part and the other file will contain the part that understands text. So this is why we need to download both of them. So if you select F16, download the text model here and download the mmproj. This is exactly what I explained here. And after that, we need to run the llama server command. This comes with llama.cpp and it allows you to host the model. Here we are going to host it locally, but you can do the same thing if you want to host it on one of your servers. And here you specify the model and the mmproj files that we have downloaded from that repository. The number of GPU layers, here it is set to 999 because this is a small model and I can fit it in on my GPU. The context size is the input that I can give to the model, and finally the port. I will copy this just to show you how this works and run this here. And as you can see, here it says server is listening on this port, which means that I can use the model. Okay, so here we have a function that will convert the image path into data URI because this is what the endpoint expects. So we give it the image path and it converts it into this format. So let's look at it just so that you can understand how it looks like. The first part is data. This is an image, and the extension is PNG. And after that, we convert the image into base 64. So this is the input that we will send to llama.cpp. Here is the port that we have specified. It's exactly the port that we can see in the terminal. And after that, we have this function that will take the model name, prompt, and image data URI. The content type is JSON because we are going to send this list of messages. You can see that we have the same thing. We have the role set to user, and we have two inputs. We have the prompt and the image. After that, we specify the max tokens to generate. We give the messages, and we send a post request to the server. After that, we decode the response and we get the content. Okay, this is how we use it. So we provide the model name, the text prompt, and when we call the extract test from images, I will quickly, or let me just put this here and open GoC on the other side of the screen, and let's run this. And as you can see, I was able to get the response in less than 6 seconds. And here it gives me that the tokens per second, the generation speed is 344 tokens per second, which is way faster than using the transformers implementation. We have this function that we can use in order to remove those tags, because if I print this, the only problem with the llama.cpp version is that we don't have those semantic or those tags that keeps the semantics. You can see that here we just get the bounding boxes, but we don't know if this is a header or a formula. So sadly, the llama.cpp implementation does not add those tags. But it's not a problem because this is just a text that we can modify later manually. We have this function that will strip those tags and will give us this. You can see this is the title, the page number, etc. And we have the LaTeX formulas. Okay, so this is how we strip the tags. And again, you can save the output if you want. And this is the code that will loop through the pages, extract the text, and append that to this variable that will contain the extract text from all pages. I am getting this error because I think what happened is that I have reassigned this variable somewhere. Let me see. Yes, you can see that here when I ran this, I have reassigned. So this output is stored here. So I need to rename this so that we don't get that error. But let me run this code that will load the file. Yes, this one. So I need to get the document and use it in that code. Okay, so let's use this document, the Rockstrix gaming notebook, and let's run this. And as you can see, here I am using TQDM in order to get this progress bar. And yeah, it seems to be working. Let's see, so let's open the text editor. Okay, so here the output seems to be good, but we have some problems that we can fix later. And here we have a lot of new lines. Something bad must have happened in this page. As you can see, this is the problem with small models, is that yes, they work most of the times, but sometimes they might break for some reason. I'm not sure, maybe because the image quality is not that great, but at least it gave us inputs that we can filter manually later. Okay, so after that we can save this if we need. The previous model that we looked at, the granized Dockley model, is, as I said, is a model that was specifically trained for this task. We have other open source models like Geometry 12 billion parameter models, the model which was created by Google. There is a bigger version, 27 billion, but sadly it is very slow on my hardware. That's why I didn't use it. And I went back to using the 12 billion. And the process is similar. You just search for this model on Hugging Face. Make sure that the name contains GGUF. And luckily Google has provided this model, which is great. So make sure to download both files and run the server, but this time use Geometry instead of Docklink. And this model is different than the Docklink model because this is a general model. It was not trained specifically to perform text extraction from PDF files, but this is similar to Gemini 2.5 Pro. You can give it a system prompt and describe the tasks that you want the model to perform. So here I am loading the same image. just to compare the result from this model to Gemini 2.5 Pro and Docklink. The system prompt that I am giving to Gematry 12 billion is similar to the one that I gave to Gemini 2.5 Pro. I'm not going to run this because it took 6 minutes. This is a dense model. The size is way bigger than the Docklink model, and it takes 6 minutes. This is why I said in the introduction that you need decent hardware to run these open source models. But I'm not going to run this, but I can just show you the output. You can see that here again we have the title. But since we have a lot of text, I decided to compare the 3 models down below. So here I'm comparing Gematry, Docklink, and Gemini 2.5 Pro. And here are the outputs. So Gemini 2.5 Pro, it perfectly extracted the text. Here I'm just looking at the first paragraph. Gematry, the output is not bad. Here, but it made some mistakes in some words. And finally, the Granite Docklink model worked perfectly, exactly like Gemini 2.5 Pro. The output was very good. So this is really, really awesome. So you can see that this model is way smaller than Gematry, but because it is trained specifically to do this task, it matches the performance of Gemini 2.5 Pro. So yeah, that is it for this video. I hope that you learn something from it. I know it is long, but I try to show everything in detail so that you don't miss anything. If you didn't understand anything, feel free to comment on this video. See you next time. In this video, we are going to take the text that we extracted with vision language models from PDF documents. This is what we have done in the previous video. But if you don't have PDF documents, feel free to extract text from Word documents, text documents, or even websites if you want. The most important thing is that we need to have text because we will take that text and divide it into chunks. How do we divide text into chunks? You might have heard about something called RAG, which stands for Retrieval Augmented Generation. In this system, you divide the text programmatically into chunks that have the same size. Let's say that you have this text. Programmatically means that you will decide to divide this text into, let's say, chunks that have 200 characters, or let's say by paragraph, or something like that. This is not a good idea because we risk losing context between chunks. In this example, the first chunk that I colored here in this light blue color ended before the end of the sentence. You can see that here it ended in this word hybrid, and the second chunk starts in the middle of that sentence. This can happen because documents can be big and you cannot control where you stop. What we should do instead is analyze the text and divide it into chunks that talk about one thing. In this example, we can store this text as one chunk because it describes a figure. This first paragraph describes the figure, and after that it tries to tell you the numbers that are inside that figure. So this can be stored into one chunk because it talks about the same thing. There is no need to divide this into multiple chunks. But how do we do that? There is no way we can achieve something like this just by writing code. But we have some options that we can try. The first one is to divide the text manually. This approach is slow and boring. The second idea, on the other hand, consists of using large language models. This method is way faster and will get you very close to the final result. The rest is on you. You need to supervise the output from the model to ensure that it can be used. Here is the flow that we are going to follow in this episode. First, you take the input text. This is what you need to extract from any document. It can be PDF, Word, text, it doesn't matter. We just need raw text. We give that text to a large language model and we ask it in the system prompt to divide the text into chunks that focus on one idea. After that, you take the extracted chunks that the model gave you, and finally, you judge that output. If the chunk is good, you keep it. But if you think that some chunks can be merged, do it. If you want to delete chunks, do it. Because at this stage, the model has done a good job. It gave you all those chunks very quickly. And now you can go through those chunks without spending a lot of time. If we wanted to do this manually, it will take you ages to convert all those documents into chunks. Luckily, we have large language models. They will help us tremendously in this task, and we just need to supervise the output. Enough theory. Now open VS Code and let's start coding. Before I start showing you the code inside the second notebook, I want to mention that I have made some changes to the previous notebook. Before, we had just one notebook, but I decided to divide it into how many notebooks? 5. So that we simplify things. So if you want to run just Gemini, go into that notebook and run it instead of running every single cell in order to get to that section that you want. So I think this way it will be easier for you to get the specific section that you need. And I have also added another model. We have NanoNet's OCR2. This model has just dropped recently and I tried it and it gave me very good results and I decided to add it. This model is bigger than Granite Dockling. Granite Dockling has 258 million parameters, but NanoNets comes in two versions. The first one has 1.5 billion parameters, but here I decided to use the 3 billion version. Using this model is easy. You just install the transformers library and there is no need to run llama.cpp or any other library. And I think I might keep adding models if I see that we have models that are very performant. I might add notebooks in this folder. Keep an eye on this. And now let's start with the second notebook. So here again, I have divided that into 2 sections. Here we have Gemini, if you want to run the proprietary model. And here we have Gemma 3. This is a language model. And here I didn't want to add more because there are a lot of language models that we can choose. And you decide the model that you want to run locally. So let's start with Gemini. As I said, we will take the text that we extracted from the previous step. And here the task is easy. We just need to write a system prompt that we will give to the LLM in order to teach it how to divide the text into chunks. Here is my system prompt, but if you want, you can change it. There is no problem in doing that. I have decided to divide this into different portions. So first I try to describe the task. This is the output format that I want the model to use when outputting the chunks. And after that, I try to add examples to show the model how to perform this task. You can read this. I will not try to read this to you, but when you download the code, you can read it yourself. But this is the first step. We need to create the system prompt. Now I will run this cell, and here I have a way to count the number of tokens. This comes from the generative AI package. Let's see how we use that. But first, let's load the text that we extracted. So here I have done this behind the scenes just to prepare this for the second notebook. And you can find this text inside the extracted text folder. So if you open the data folder, you'll have everything here. So I'll try to store the extracted texts here so that you can run the notebook without any issue. And here I have added, so here, this is the document that we worked with previously, the scanned PDF document. And here I added the original one, which is unscanned, and it contains, I think, 110 pages or something like that. So that's why we have 85,000 characters. So this is the one that I am using. So now let's count the number of tokens. Luckily, it's simple. So here you call the count tokens method and you provide the model. So here, because we are using Gemini 2.5 Pro, this is what we are going to use. If you want to experiment with Flash, change the name here. And after running this cell, let's see what we get. So we have 8,000 tokens in the prompt. and 18,000 tokens in the text. So in total, the number of tokens that we will send as input is 26,000 tokens. Why am I showing this? This is very important, especially if you want to run models locally, because when you increase the input, you will need a lot of memory. Just keep this in mind. But here, since we are using Gemini, there is no problem because we are going to run this query will be executed in Google's servers. And now we are going to create a pydantic object. A pydantic object is going to be used by Gemini to force it to output a valid JSON. As you can see, each chunk in our JSON output will have just one field, the text chunk. And this is similar to what I have mentioned in the system prompts. Let me go back to the system prompt just to show you where I have added that. It's here. So in the output format, you can see that each object contains one field, the text chunk. And this is what I have created here in this pydantic class. We have just a base model that contains one field, and I call this text chunk. Let's run this cell. Now we are ready. So we have the prompt, we have the extracted text. Now we have everything to start extracting the chunks. And here, this is where we are going to use that class. So here in the generative AI package, we have the ability to specify that the output should be a JSON, and because we will receive multiple chunks, we want the output to be a list of these classes, of this class. So every object in this list will have just one field, the text chunk. And the max output token, I have set it to the max value, 65,000, just in case. Okay, now we can run this and let's wait for it. The request took almost 3 minutes. The time will vary depending on the size of the text. Here, as you saw, I am working with a very big document. That's why this request took 3 minutes. But if you are working with small documents, it shouldn't take that long. We have access to this parsed attribute. The great thing about this is that it will parse the output and give us pydantic objects. So let's run this. As you can see, the number of chunks have changed because the models are not deterministic. Each time they will give you something different. And here, these are pydantic objects, so I can look at them. Let's take the first chunk. And as you can see, it has just one field. So now I can do this and get the text chunk. Why is this better than, let's say, not using pydantic objects? From the response, we can, instead of getting parse, we can get text. And this is what we will get. Now we need to do that parsing by ourselves. That can work, but sometimes the models might fail to output a valid JSON. But luckily, Google have this implementation that guarantees that the output will be a valid JSON. Okay, so we got 63 chunks. Now let's look at the number of tokens that the model has generated. So you see the input number of tokens is 26,000 and the output we have almost 20,000 tokens. So in total we have 46,000 tokens. So that's a lot. So keep in mind that if you want to use this locally, you need to have a lot of VRAM in order to handle this amount of tokens. As I have mentioned, we can get the text by accessing the text chunk attribute from each class. Here I am looking at the first chunk, and here if you don't remember, let me show you the document. So it's rog strix. Let's look at the unscanned. Let me put it here and let me go to the first page. You can see this is the cover page, and here the model extracted this text and it stopped. That makes sense because this is the text that we have in the first page. After that, we have the table of contents, etc. And here 10, I think, let me look at it. So it's battery safety information. Okay, so it's in this page. So it took the title, the subtitle, it took everything, frequently charging, it took the notes, etc. It also took this part because all of these things talk about the battery safety information. and then it stopped right here. So let's verify that. Yes, leakage that may cause fire. That may cause fire. So that makes sense. So the model took all these parts. In some scenarios, maybe the model will take this as a chunk and this as another chunk. And you'll decide if you are fine with that output or if you want to merge them both, like what has the model done here. Okay, so it seems to be working. And now we have our chunks. Let's see what we will do with them. Now we need to save them. Okay, and here we are going to add an ID. I'm going to explain this in the upcoming video. So basically, in the upcoming video, we are going to generate question answer pairs. And for each question, we will have a chunk that will answer it. And in order to link them together, we need to have an ID, a way to identify a chunk. And this is how we are going to do it. We already have the text chunk, but let's also add the ID. So now if I run this and look at text chunks dictionary, let's look at the first one. As you can see, so this is the text and this is the ID. So we will do this just to prepare for the next video. And now we can save it inside the chunks folder. I have already done that. So if I open the chunks folder, this is what I get. So these are all the chunks that we will save for each document, and later we will merge them together into one big file. So let me close this one. I don't want to save it because I don't want to push those changes. And now let's open the open source model. Here I chose geometry and I am using one of the smallest models, the 4 billion model. Like before, let me show you the steps one more time. So you go to Hugging Face. For example, here I am looking at the model in the ggml.org repository. You go to files and here you choose a quantization level. This choice depends on the amount of resources that you have. So you can go with Q4 or Q8 or F16. This is a this is a multimodal model, which means that it can process both text and images. And for these types of models, you'll have two types of files that you need to download. You will need to download the mmproj file for the vision capability and one of the other models for the language model. So here you click on this one to download the mmproj and choose one of these. If I go back to VS Code, you will see that this is what I have mentioned in this text. So for example, here I chose Q4 and the mmproj file. And after that, you start the Llama server with this command. If you don't want to use geometry, but you want to use, let's say, Qwen or other models that only process text, you can do that. And those are simpler because you will download just one file. Let's look at Qwen as an example. Okay, here is Qwen tree. I can click on it. Let's look at this, the 4 billion one. Let's look at files. And as you can see, there is no mmproj file. You need to download just one file because this model does not have the ability to process images. Let me also run the server in the terminal. Here, this will not work for me because I need to change the name of the models. Let me do that quickly and I will come back. I am back and I have changed just the name of the files. Now I can run this. Here, make sure to change the number of GPU layers. Here, this model is small, so I chose 999, but if you are working with bigger models, change that so that you don't get an out of memory error. Okay, so now it says listening on this port. Okay, that's good. Now we can go back to the code and let's start. I took the same system prompt from the previous notebook. Here, we cannot use we can use the generative AI library to count the number of tokens, but every single model has a different tokenizer. So we need to use the tokenizer that comes with the model. And luckily with llama.cpp, they have the tokenized endpoint, which will take the text and tokenize it. So if I run this, you can see that here we are using the same port, 36912. You can change this, set it to any port. And after that, so we tokenize the prompt and we get the length. So this gives us 26,000 tokens in input, which is a lot, which is similar to what we got with the Gemini tokenizer. And now I have modified this function slightly so that we can stream the output. I have added this because running these models on my hardware, it's a bit hard. Even though the Gemma 4 billion model is small, it's still not fast. I'm getting 20 tokens per second. It's decent, but it's not the best. As you can see, so the generation is great, but since we have a lot of text, that will take minutes. But let me show you what we have here. So I have also added a user prompt, which basically tells the model that I want you to carefully split the document into coherent chunks. So yeah, basically you can read this. And I have stated that I want only JSON array. And I am using the same text from that document that contains 110 pages. And the problem that I'm facing with geometry is that, look, it finished. It says that it finished in 34 seconds. But if I look at the output, and another problem here is that we cannot use pedantic objects. So we will need to parse this ourselves. So that's not a problem, we can do that. But if we count the number of chunks, we will see that we have 1, 2, 3. So here's the table of content, and then it will stop. So I have tried to basically play with the prompts, but I couldn't get this small Gemma 3 model to do this task for me. So the only thing that you can try is to use this model with small documents. Here, I didn't want to, let's say, take 10 pages, feed them to the model and get the chunks, because we will lose that context. For example, with Gemini, I wanted to give it the document and let it decide how to divide it. With Gemini, with this small model, I couldn't do it. But I have tried the Qwen, the 30 billion model. That one worked very well. But the problem, the generation speed was way slower. I was getting 5 tokens per second or something like that. So if I wanted to wait for this model to finish chunking this document, that will take hours. But at least I've tried to write this notebook for you. If you have more GPUs than I have, then in your case it will work very well. But in my case, I couldn't rely on these open source models because I don't have the right hardware to run them on. But yeah, this is the idea, and hopefully you understood how we divide the text into chunks. But as I said in the slides, there is one more step that you need to do. You need to verify the output. So you need to verify if these chunks are correct. Do you need to merge chunks together? Do you need to delete some chunks? You decide. So yeah, this is the last step that you need to perform, and this should be done manually. We will not ask the model to do that for us because the models are stochastic, and here we are not going to try to generate millions of chunks or millions of question-answer pairs. We will just generate maybe 500 or 1,000 maximum. And yes, this is going to take a few days of work. I have done this at my current job, but in the end, you will get a high quality data set. It's way better than giving the LLMs to do all these tasks for you. That's it for this video. See you in the next one. In this video, you will learn how to generate question-answer pairs from the chunk that we created in the previous step. In this step of the pipeline, you are going to generate questions that can be answered by a chunk of text. Note that a chunk can answer one or more questions, and a question can be answered by one or more chunks. Here's an example. I took this chunk of text that describes the bits and bytes Python package. And then I asked a large language model to give me questions that can be answered by this text chunk. It gave me more than 2 questions, but I just took these 2. And the most important thing is that in this step, we need to validate these questions. They need to be relevant to the chunk. For example, here I can start to read. Here, bits and bytes enables accessible large language models via k-bit quantization for PyTorch. And the first question asks, what is the primary purpose of bits and bytes? And this can be answered by the first sentence of this text. And after that, the text says, bits and bytes provides three main features to reduce the memory consumptions. And those are 8-bit optimizers, 8-bit quantization, and 4-bit quantization. And the second question asks, what are the three main features bits and bytes provide for reducing memory consumption? And the answer to this question is what I have just read right now. So you can see that the questions that the model generated, they are valid and we can keep them. And because this is a simple task, it is guaranteed that a large language model will give you very good answers. So that's it for the theory. Now let's code. Before I show you the notebooks that I have created for this video, you will find the source code on this GitHub repository. I will make sure to put the link in the video description. So please take the source code and play with it while watching my explanation. Now let me open VS Code. Here are the notebooks. I have two notebooks. Like before, we will keep doing the same thing. We will have one notebook for proprietary models and one notebook for open source models. And here, the proprietary model that I chose is Gemini, but if you want, we can easily switch to other providers. So the third notebook will allow us to generate question-answer pairs. In the previous step, we have saved the chunks inside the chunks folder. I have done this for the Rogstrix document. And here I have, I think 43 chunks. When you clone the repository, you will be able to access this JSON file because I have pushed it to the repo. Now we will take these chunks one by one and we will ask Gemini, and here I chose Qwen for the open source model, to give us the questions. Let's see how we do this. So first of all, we start with the system prompt. These are simple tasks that can be performed just by playing with the system prompt. I started by describing the task. So I told the model that you are an expert at generating relevant questions given some chunk of text. And after that, I tell the model that this is very important for creating question-answer pairs. Basically, I describe the task. You can describe it however you like. But what's important is telling the model the output format and giving it examples so that it understands the task. So the output format is going to be a list of JSON objects, because this is what we want. We want multiple questions per chunk, and each question should have this field. It should have just one field called question. So this is the output format. And after that, I immediately give the model examples. Here I took the same text that I showed you in the slides, that talks about the bits and bytes library. And after that, here is the output. I have another example, which is much longer than the first one. If you don't give the model examples, it might behave differently, but the examples will help you guide the model, and the model will always behave the same way because it will try to mimic the examples that you gave it. Let me run this cell. At the end, I have a notes section where I tell the model to not generate questions that are similar to each other, because sometimes the model might give you two questions, but if you look at them closely, you will see that they are basically the same. And here I also say to stick to the JSON format, and the questions should be relevant to the text. After that, we will create a Pydantic object, because we saw in the previous video that Gemini can accept Pydantic objects as input to basically guarantee that the output will be a valid JSON. And here, because I have just one field, this is why I have created this class with one field called question. Now we can use Gemini to give us a list of questions. Here I created a function that will generate those questions. It will take the text chunk, the system prompt, and the model. By default, it is set to Gemini Flash. We will send the request and receive the questions. Inside the generate content method, we provide the content. The content will be the system prompt and the text chunk. In the configuration, we mentioned that we want a JSON. It is here that we use the pedantic class. And here we tell the model that we want a list of this object. After that, when we call the parse, when we get the content of the parsed attribute, it is guaranteed that it's going to be in this format. Now let me run this cell and let's go. I have created this function because we will be calling it for each chunk, and after that I will have a for loop that will call that method. But before using the for loop, we need to load those chunks. As you can see, we have 43 chunks. This is what I showed you in that JSON file. And now we can use that function. So we are going to loop over those chunks, and the chunk is an object. Let me open the JSON file again, just to show you what it contains. So each object has two fields, the ID and the text chunk. I told you in the previous video that this ID will be used in this step. And let me show you how we do that. So we get the text object. From that, we can extract the text chunk. We are going to give it to the generate questions method. And after that, we will get the list of questions. And here we need to link the questions to the chunk. That's why we needed that ID. And here, after getting the questions from Gemini, we are going to link them to that ID. Let me run this one time so that you can see what I am talking about. And here I have added this time.sleep because if you are using the free tier, you will get rate limited quickly. So this will prevent you from getting rate limited. But if you are using a paid API key, make sure to remove this line so that this process will not be slow. Let's look at the question answer pairs list. Or first of all, let's look at the questions. As you can see, this is a list of this question class. And if we look at the question answer pairs, as you can see, all these questions are linked to the first chunk. And this is going to be used in one of the upcoming videos. So we are just preparing the data to be ready for the comparison later. And now this will loop over the chunks and store the questions and link the questions to that chunk. I have already done that, and I was able to generate 266 questions from all those 43 chunks. And after that, I have saved them inside another JSON file inside the question answer pairs folder. Let me show you this file. As you can see, so here we have the first questions that can be answered by the first chunk. We have, in the second chunk, we have how many? 1, 2, we have plenty. 1, 2, 3, 4, 5, 6, 7, 8. So in the second chunk, we have 8 questions. Now we have seen how to implement this with Gemini. Let's go to the other notebook in order to show you how to implement this with any open source model that you can run locally with either llama.cpp or transformers. So let's look at this notebook. I chose to use the Qwen3 model. This is a model that I can run locally, and you can find it on Hugging Face. Let's click on this link because I want to show you again how to download these kind of models. Here is the repository, and here you can see the quantization levels. And if it is red, it means that you will not be able to run it. But if it is green or orange, that means that you will be able to run it. But because we are going to use llama.cpp, even if it shows you red, that does not mean that you cannot run it, because you can split the model. You can run some layers on the GPU and the other layers can be run on the CPU. And if I switch to, for example, here I have CPU with 40 gigabytes of RAM, you can see that now all of them are green, which means that I can run them. I chose the Q4 version, Q4KM. So you can click on it to start downloading, or if you have more GPU VRAM, you can go up to Q8. Let me go back to the notebook. So this is what I have mentioned here. After you download the model, you need to run the server. So let me take this command and run the server in the terminal. Let me zoom in and paste the command. I am not using 999 in the number of GPU layers, but instead I am using 18 because I cannot fit this model entirely on the GPU, as you saw on Hugging Face. But 18 works fine. If you go lower, the model will start to become slower because you will start to upload more layers, a few layers to the GPU. But in my case, 16 or 18 works fine. But I need to keep some memory for the context. So I'll just upload 16 layers. You need to see this message. Server is listening on a port. I chose this port, but you can choose any other port you like. Good. Now we can run the notebook. So after that, I took the same system prompt. So nothing changed here, but I am also creating the Pydantic object. But the only thing that will change is how we call the model. We are going to use that endpoint with that specific port that I have used in the llama server command. And here, this is how we generate text. We are going to call this endpoint v1 chat completions, and we are going to give it two things: a list of messages and the maximum tokens that we want to generate. But what's important is the list of messages. First, we set the role to system and put the system prompt there. And in the user prompt, we will have the text chunk that we want to extract questions from. And after that, we send the post request to this endpoint, and we get, and from here we get the assistant message, which is basically the reply that contains the questions. And because here the output will be a string, we need to parse the output manually. This is why we are passing that message to the parse questions method. Let's look at it. So because that's a JSON, and hopefully it should be a valid JSON, because the output will not be very big, so the model should be able to output a valid JSON. If that's the case, the JSON.loads method will not throw any exception, and then we are going to create instances of the question class. So let me run this just to show you how this works. After that, we load again that JSON that contains the chunk, and here we loop over the chunks. And here I also have this getUserPrompt method. You can add some text before and after that text chunk just to simulate the user's turn. So inside the loop, we get the text chunk, the user prompt. We pass them to the generate questions method, and the rest is the same. Now, let me run this just once to show you the output. And if I open the terminal again, you can see that we were able to we received the request, and here, as you can see, the generation speed is 15 tokens per second. Let me decrease the font. Yeah, this is better. The generation speed is 15 tokens per second. That's not bad. And let's go back to VS Code to see what we got. Let's look at the length. We got 5 questions from the first chunks. Let's look at them. And the output looks similar. We have the question and we link it to that specific chunk. And finally, we save the question answer pairs inside the question and answer pairs directory. So as you can see, it is very simple to run local models, and I am 100% sure that they are going to perform very well in this task because it is not a very complex task. And if you want, you can change the model. You can also try the Gemma models or GPT OSS if you want. So feel free to try any open source model. You know how to download GGUF files. So try them and see if you can get good results with other models. This is it for this video. In the next one, we are going to talk about embedding models. In this video, you will learn about embedding models. We will use them to turn the text chunks and questions we created earlier into numerical representations that a computer can understand. A text embedding model converts text into a numerical representation. For example, if we give a piece of text to an embedding model, it returns a list of numbers. This list is called a dense vector and it contains n numbers. What is the purpose of an embedding model? This graph helps explain the main idea. Let me walk you through how I created it. I wrote a few sentences about two topics, space and cooking. Then I converted each sentence into a dense vector. Since these vectors contain hundreds or thousands of numbers, we can't plot them directly in 2D. To fix this, I used a technique called t-SNE to reduce the dimensions to just 2, making it possible to visualize the data. As you can see, there are two clusters. The blue dots represent the space sentences and the red dots represent the cooking sentences. The model I used did a good job. It placed similar sentences close together and pushed different ones farther apart. Here is an example of one phrase from each cluster. In the space cluster, we have how far is the Andromeda galaxy, and in the cooking cluster, we have how to cook a perfect steak. Notice how these two sentences are far apart. If you try the same example with a different model and see that the sentences are close together, it means that the model is not very good. The main goal of an embedding model is to preserve the meaning of a piece of text. This allows us to build useful applications like recommendation systems, retrieval augmented generation, and much more. Earlier, I mentioned that the output of an embedding model is a dense vector of size n. But does the size of this vector really matter? Let's look at this table to understand better. For large values of n, you can capture more subtle differences in meaning. This is very helpful, especially when sentences are similar but have slightly different meanings. You can also identify finer details within the data, but the problem is that larger embeddings need more computational power. They also take up more storage space since the vectors are big, and finally, when we perform similarity searches, they take longer because of the higher latency. For smaller values of n, they need fewer computational resources, they are faster to process, they take less storage space, and have no latency issues. But the main downside is that smaller embeddings can't capture as much detailed information as larger ones. So there is a trade-off between the two. If you are working with complex or multilingual data, larger embeddings are usually better, but if your data is simple and in one language, smaller embeddings will work just fine. To be clear, small embeddings usually have fewer than 1000 values, while large embeddings can have 2000 or even 4000 values. Here are the models we will be using in this video. I highlighted the all-mini-LM model because it has the smallest embedding size, 384, and the Qwen3 embedding 8 billion model because it produces very large embedding vectors, and the size is 4096. The other models fall somewhere in between. In this list, we have open weight models and closed source models. Let's see how much space it takes to store 10,000 vectors in a vector database. Notice the big difference between the Qwen3 model and the all-mini-LM model. Qwen3 needs about 11 times more space than all-mini-LM. And here the size is in megabytes. And if you plan to store 100,000 documents or millions of documents, that number will grow very rapidly. Keep this in mind when choosing an embedded model, especially if you are working with large datasets. You can use either open source or closed source models depending on your situation. If you don't have the necessary hardware to run open source models, you can use models from providers like Google or OpenAI. But if you have the required hardware, you can run, for example, the All-Mini LM is very small and you can run it even if you don't have a GPU and you have just a CPU. But the Quentry model, that's a big one, so you will need to have a GPU in order to run it. But even if you go with, let's say, closed source models, they are very cheap. I have mentioned this in the beginning of the course, but you can use the MTab leaderboard to find the best embedded models available. Here is what the pipeline looks like after adding the embedding step. It may seem a bit complex, but let me explain it step by step. We start with the text that we extracted from a document. We use an LLM to split it into chunks. After that, we use an embedding model to convert each chunk into a dense vector. These vectors will be used in the next video. Next, we send the extracted chunks to another language model to generate questions that can be answered using those chunks. This is what we did in the previous video. We then pass those questions to the embedding model to get another list of dense vectors, which again we will store for later use in the next video. So this is the pipeline, and in this video we are going to work on this step. Now let's start coding. Here are the notebooks that I prepared for this video. We have 7 notebooks that will show you how to use open weights models and closed source models. The source code is on GitHub. You can find the link in the video description. Let's start with Gemini. And here we are going to convert both the text chunks and the questions. So let's look at this. I will close the Explorer and start with the first notebook. First, we start by loading the text chunks and the questions that we stored in the chunks folder and question answer pairs folder. Let's run this. And these files, you should be able to get them when you clone the repository. After that, we are going to embed the text. Here we use the embed text method. It's going to call the embed content method. Here we are going to pass the embedding model. And with Google, they have this model, Gemini Embedding 001. If you go to the leaderboard, you will see that this is one of the best performing models in that table. And yeah, it's simple to use. And after that, when you get the result object, you can access the embeddings. And here you can pass multiple text at the same time to run this in batch. But in my case, I am just getting the first value because I'm doing it sequentially. But if you want to optimize this, you can provide a list to that function instead of just a string. So after running this, you can see that it ran. And I've also added the time.sleep because with Google, they allow you to try their models for free. It's not like OpenAI or other providers. They don't have a free plan. So here, if you just want to try this, you can create a free API key and use it here. This is what I have done. And I have added the time.sleep so that you don't run into rate limits. But if you have a paid subscription, then remove this line so that the code runs quickly. And here I have just added a list to store any if we got any error, but luckily I didn't get any, so I was able to embed all those chunks without any issue. And after that, I do the same thing for the questions. So I take the questions list, I take the chunk ID and the question from that object, I pass the question to the embed text method, and I get the embedding for that string. And then I store everything inside the same object. So let me run this just to show you how this works. So here, instead of running the embedding model on all of the chunks. I will just run it in one iteration just to show you what we'll get in the output. So let's run this and wait. Okay, so it's finished. That's great. Let's look at the text chunk embedding. So if I try to print this, you can see that this is a list of numbers. Let's look at the size of this vector. Okay, so as you can see, we have 3000 numbers in this vector. And now what we'll do is that we already have the text chunks list, and we use that in order to insert the embedding vector inside the same object. So let me show you what I'm talking about. Here, if I look at the first element in that list, you can see that originally we had just ID and text chunk, but now we also included the embedding. And I can show you the keys directly. So yeah, this is how it looks like after running this. We are not creating a separate list, but we are referencing the same object in order to include this new key. And we do the same thing for the questions. If I come here and add a break statement just to stop the code from running multiple times, you will see that we take the questions list. Let's look at the first object and let's call keys, and we get the same result. So now we have successfully converted the strings into embedding into dense vectors. Now we can merge the two lists. Here is the structure that we are going to follow. We are going to have one JSON file that will contain the chunks and the question answer pairs lists. And inside the chunks list, we will have the same schema. We will have the ID, text chunk, and embeddings. And inside the embeddings, we will try to store multiple embeddings per model. So here in this notebook, we are going to use Gemini embedding. So we will add that. But after that, when we switch to Qwen, we are going to add that inside the embeddings dictionary. This way, we will be able to compare these embeddings in the upcoming videos. And if we look at the question answer pairs, you see that we have the same structure. Here, chunk ID references the ID of the chunk so that we can link them. And here the question. Basically, chunk ID will be the answer to this question. And inside the embeddings field, we will store multiple embeddings. Okay, let's get started. So I am going to create an embedding folder inside the data directory. As you can see, here it is. Inside that, we are going to create an embeddings.json file. So first of all, if that directory does not exist, I'm going to create it. After that, I create the file name. And if it does, here we need to be careful. When you are going to start this file will not exist. So if voice.path.exist will be false. In that case, we will go to the else statement or to the else case. And here we are going to start fresh. We don't have any file, so we'll have empty lists, and then we will start populating them. And here we have two for loops. The first one will loop over the text chunks so that we can populate the chunks field. And the second one loops over the questions list in order to populate this field. And here we are not using zip to have just one for loop because the number of items inside text chunks is not equal to the number of items inside questions. If I go up, you see that we have 43 and it's different than 377. So don't use zip in this case. And now we are going to populate this and we are going to follow the same schema. So we will have an ID, a text chunk, and embeddings is going to be a dictionary with individual models. And here, since we are using Gemini embedding 001, we are going to use that as the key. And we do the same thing for question. We put the chunk ID, question, and embeddings. And here inside embeddings, this is a dictionary. This is important because it will allow us to compare different models. We are doing this so that we can store everything inside one JSON file instead of creating multiple JSON files for each model. So it will simplify reading data in the upcoming steps. So as I said, this will run only if the file does not exist. But in my case, since I already have it, this code will go through the if case. So if that file exists, I'm going to load it. So after loading that list, I'm going to start overriding the items. So here you can see that I'm looping over the text chunks. I'm accessing the chunks list. I go to the ith element and override the embeddings for that specific model. And this will work if the file exists. If it doesn't exist, then this should not run. And we do the same thing for embedding. So this is how we create that JSON file, and at the end we store it. And here I want to mention something. If you decide to make some changes to the files, let's go to the text chunks just to show you what I am talking about. So if I decide to go here and change the questions, this means that I need to regenerate this JSON file, and the code will not try to magically understand what you have done in order to apply those changes to the JSON file. That will be too much work, and the easiest thing is to just delete this file that you generated inside the embeddings directory and rerun the notebook. But if you decide to change the chunks, if I go to the chunks folder and open that JSON file, if you decide to remove chunks or merge chunks together, in that case, it's more complex. So you will need to generate the questions and then regenerate embeddings. So these steps are dependent on each other. If you remove one, you need to update the ones that are after it. I hope that this is clear. So yeah, this is how you do this with Gemini. As you can see, it is very simple to work with embedding models. You just give the text and get the dense vector in the end. Okay, so I will not save this notebook because I don't need to save these changes. But now let's go to, let's go to the OpenAI models. I want to start with closed source models, and then I will move to the open weight models. So with OpenAI, we have two versions. The first model is small and the other one is large. So let's start with the small model. First, we start by loading the data. Let's do that. We have 43 text chunks and 357 questions. And as I said, with OpenAI, you don't have a free API plan, so you need to pay for it. But as I mentioned, embedded models are very cheap. Here, if you put 1 million tokens, that will just cost you $0.02. That's very cheap. And 1 million tokens, it's a lot of text. And if you decide to use batch, it's even half the price. So even if they don't have a free plan, this is basically, this costs me nothing. You'll see that below. I mentioned that I've run this and I have done the calculation, and here it is. So the total tokens that I have in everything, in the text chunks and in the questions, is 23,000 tokens. So this costs me $0.000464, which is basically nothing. This is why I said that embedding models are incredibly cheap. And in order to use their models, you need to install the OpenAI library. And I have made sure to update the requirements.txt file. So as you can see, we have the OpenAI dependency here. So if you run pip install -r requirements.txt, you should have it. And here it's similar. So you use the client, the OpenAI client, and you use the embeddings API, and you call the create method. You give it either a text or a list. Here I did the same thing with Gemini, so I provided just a string, and I will get just one value. This is why I am accessing the first element in the list. And I get the embedding. If something bad happens, I will throw an exception so that I know that something went wrong. And here are the models. So they call them text embedding tree small, and the large will be text embedding tree large. So we loop over the text chunks and we generate the embeddings. Let me do the same thing. So here I will add a break. And as you can see, I removed the time.sleep because I am paying for that API, so there won't be any issue. Okay, let's run this and let's look at the text chunk embeddings. I would look at the length of this. I don't want to look at this, but I want to look at the length of that dense vector. and it's smaller than the Gemini model, so the size is 1536. Okay, we can do the same thing for the question and we will get the same result. And after that we have, so here is the code that I have used in order to calculate the cost. I am using the tick token library. What does it do? Let me show you what it does. So here we have this get encoding method that will convert a string into a list of tokens. Let me show you how that works. So if I call the .get encoding method, I need to give it an encoding name. So that's here, this is a dictionary that contains tokens, and I can access it like this, and I can use that encoding in order to encode a sentence. So let's just try to encode. So here it's giving me an error because I need to import the tick token library. And here let's encode, for example, hello world or something. Hello world. And let's look at the output. So hello world was divided into 4 tokens. And these are the tokens that are used in order to calculate the cost. Because these models don't work with text, they work with numbers. And in order to convert text, they use tokens. Okay, so now let's go here. So this is what we are doing here. Number of tokens from string. We provide a string and we get the number of tokens. And after that, we loop over the text chunks and questions and start calculating the number of tokens. And after that, here I am not using batch. This is why the cost will be $0.02 per million tokens. And yeah, if I run this, it should give me the same price. Awesome. So now let's go down, and here this section will be the same. So we are going to merge the lists. And now, since we have generated that JSON file, this block will not run, but this else block will not run, but we will be able to run the if clause. And here we are just going to go to each element where we stored the Gemini embeddings, and we'll add inside the embeddings dictionary the OpenAI model. And after that, we will save that JSON. Now let me show you that JSON because I keep talking about it, but I haven't showed you how it looks like. So here it is. It's going to be a big file. Let me show you the size. So it's 137 megabytes because I have embeddings for 7 models. And yeah, so let's try to render it. It takes a while in order to format the JSON because it's too big. And VS Code crashed. Okay, next try. So let me save it. Okay, so it didn't work. It says that this file cannot be formatted because it is too large. Okay, that's sad. So yeah, it was working before when I didn't have 7 embeddings inside each object. But let me try to find another way to solve this. Okay, so let's do it with code. If the formatter can't handle big files, we can do that inside the notebook directly. I've loaded the data and we have the correct number. Let's look at chunks, for example. Let's look at the first chunk, and here I want to look at the keys. So let's print the keys. Okay, great. So we have the embeddings. Let's dig deeper. Let's go to embeddings because this is what I want to show you. Okay, let's look at embeddings and let's print the keys. And voila, you can see that we have all our embedding models. So we have the all mini LLM, the Qwen models, Gemini, and the OpenAI models. And this is going to be very helpful in the next step where we are going to benchmark these models. So we are very close to comparing them. Great. And if you are curious, we have the same thing inside the question answer pairs. Now let's close this notebook and open the other one. And let's look at the large one because the pricing is a bit different. If you want to embed 1 million tokens, then you will spend $0.13. And let me show you how much it costed me to do all of that. So it's $0.003. And again, this is very cheap. The cost will start to increase because this is just a document, and we need to generate a few more chunks. But still, you will not reach $1 because the models are so cheap. And yeah, the rest of the notebook is the same. So I'm not going to waste your time just to show you the same thing. Now let's go to the open source models. And I will start with the smallest, the All Mini LM. This is one of the popular embedding models on Hugging Face. Let me show you the model card just to understand why am I saying that it is one of the most popular embedding models. So if I look at All Mini LM, yeah, we have many versions, but the L6 is the one that is used the most. As you can see, it has been downloaded almost 140 million times in the last month. Why? Because this model is very small. It has just 23 million parameters. And yeah, it gives small embeddings, but at least it's usable. And in order to use it, you use the sentence transformers library. I have also added this inside the requirements.txt file. So if you reinstall the dependencies, you should have it. And here, if you don't have the model, this library will install it and then put it in the cache. So that's why it didn't take me too long to download it. And here I am running it on CUDA. But if you don't have GPU, the code will fall back to use a CPU. Again, we load the data, and here, this is how we use the model. It's simple, it just has this encode method. And again, you can either pass a string or a list. And you use the model like that. And let me show you, because it's small, it's so fast. So we were able to embed those 43 strings in less than a second. And I can do the same thing for the questions. Boom, it's done. So it took less than a second to embed almost 400 questions. And let's look at the size of the embedding, because this is the big difference between this model and the other ones. So if I try to print this, you can see that the size is small. It's 384. Okay, the rest of the notebook is the same. We merge the lists and we store the embeddings. Now, let's go to the last model that I tested, which is the Qwen model. And here we have 3 variations. Like the OpenAI model, we have small, medium, and large. So the small model is bigger than the All Mini LM. So this one has 600 million parameters. And in order to use it, again, you use the sentence transformers library. Let's do that. And this one will be a bit slower, but still usable. Especially if you have a GPU, it will run very fast. Let's wait for the model to load. That's done. And let's go and try to embed the strings. But there is something interesting with this model from Qwen. You can prompt it. Instead of just giving it text, you can also prompt it by giving it instructions. And here by default, the model comes with this prompt. So the query is this: given a web search query, retrieve relevant passages that answer the query. This is going to be helpful for retrieval augmented generation tasks. And after that, you pass the document. And if I run the for loop, you'll see that it's going to be a bit slower, but still usable. And if you don't have a GPU, this will definitely take more than 5 seconds. Let's do the same thing for the questions. So here, as you can see, it runs very fast. And we can also make it even faster if we provide this function with a list instead of a string. That will make it faster. But here I'm just doing it sequentially, just to make things simpler. Let's look at if we have anything that failed. No, nothing failed. The rest of the notebook is the same as the other ones. Now let me restart this because I want to free up VRAM, and let's go to the medium and large models. These are very big models that are hard to run locally. So the medium model has 4 billion parameters and the large model has 8 billion parameters. And both of these notebooks are similar because here I am using llama.cpp like we did before in order to run these models at low quantizations. Because if you try to run the full model, you'll need a lot of VRAM. And in my case, I can run the 4 billion parameter model, but the VRAM, I don't have a lot of VRAM. I have just 8 gigabytes of VRAM, and that's not enough. But lowering the quantization helps definitely to solve that issue. So let me show you again how to do this. You need to download the GGUF file from Hugging Face. Luckily, the Quen team has created those files. So here, for example, for the medium model, you can come here and download one of the quantizations. I went with Q4KM, but if you have more VRAM, you can also load the Q8 or F16. After loading that model, you need to put it somewhere. I always put the model inside the cache, and here is the command that you need to run. We use llama server, but since here we are going to work with embedding models, we need to add the embedding argument and pull in CLS. And here, since the model is big, you need to play around with the number of GPU layers. Here I have set it to default 999, but you will get an out of memory error if you don't have enough VRAM. Okay, because the Quen tree embedding model can accept texts that are up to 32,000 tokens. That's great, but if you try to encode those, they will require a lot of memory. I will show you how this works. By default, if I try to run this, okay, so it worked, but if I try to encode or if I try to embed the text, I will definitely hit an out of memory error if I have a big chunk of text. Okay, so the server is running. Let's see if it's going to work or not. And now here is how we use the embedded model. So we use the embeddings endpoint. We don't use the completions endpoint. That one is used just for large language models. Instead, we use the embeddings endpoint. After that, we put the text. This is the only input that an embedded model accepts, and we get the embeddings. And again, we are not using batch implementation. We are just going to get one item in the list. So let's create that method. And after that, we load the data. And now we are going to run it. So this is the Quen model. Let me add a break just to see if this is going to work. Let's look at the terminal. And we received the request. So it's a post request and the response is 200, which means that nothing bad happens. So we were able to embed that. Let's look at the length of this dense vector just to confirm. And yes, everything worked properly. So the size here is 2560. That's bigger than all mini LM model. And you can run, let me run this because I know that I have a big chunk that will give me an out of memory error. So all of these are small. Yes, but this one is big. Okay, so it passed. So that means that I have enough memory. But yeah, if I try to run the same thing with the 8 billion model, it will definitely stop running because I have, this one will consume double the memory that the 4 billion model consumes. Okay, so let me show you that just so that you understand how to resolve these issues if you get them. And the rest of the notebook here is the same. So let me close this and go to the next one in order to show you how to troubleshoot the out of memory error. Open again the terminal, and here instead of running the 4 billion model, we are going to run the 8 billion model. And again, you can click on this link in order to download it. And here is the page on Hugging Face where you can download that model. Okay, now let's run this in the terminal. Make sure that you are using the 8 billion model. The context size is the same because I know that there is a chunk that is very big. It contains, I think, 4,300 tokens, and that one was causing me problems. That's why I have increased those three values to around 6,100 just to account for that one. And as you can see, we were not able to allocate that memory needed for that context. So in this case, I need to go up and decrease the number of GPU layers. So 999 basically will offload all GPU or layers to the GPU, but I need to decrease that. So and here you do this just by trials and errors. So I will try maybe 30. That didn't work, so I will go back and start decreasing it until it loads. So let me go to 20 and try to not go too low because you don't want to offload less layers because in that case the model will be slow. In my case, let me show you. So if I go here and use NV-top, you can see that here is the amount of VLM that is consumed. So it's 7.5 gigabytes. So that's, let's see. So if you look at the graph, you can see that it's almost 100%. So this is what you want. You don't want to use just 50% of the memory because that will be slow. So if you look at here, it says 85%. Or if you don't have NV-top, you can just use NVIDIA SMI. Okay, let me decrease the font. And as you can see, here is the process. So Llama server is consuming 7 gigabytes of VRAM error. So this is how you debug this. And now if I go back, I should be able to run this model. So let's go quickly and let's do this. Okay, so it's a bit slower, but it's usable, and you are running things locally without any issues. Yeah, most of the chunks are small, but there is one that contains a whole chapter, I think. That's, yeah, this one. So this one takes a while to embed, but it worked. If you don't have big chunks, you can decrease these so that you can increase the number of GPU layers. So that's the last notebook, I think. Yeah, this is the last notebook. And in the end, we end up with this file inside the embeddings folder. And as you can see, I have ignored this directory. So if I go to the .ignore file, I have ignored it. Why? Because the size of the file is big. So it's almost 200 megabytes. And I will be adding more documents in the upcoming videos. So basically this folder will hold 1 gigabyte of data or more. So that's why I can't put this on GitHub, but I will see if I can put this on Hugging Face or Kaggle so that you can download it directly, so that you can use it in the next steps if you want to go quicker and not run these. But I highly suggest you that you go through the notebooks, at least run if you don't want to run the OpenAI models, if you are just trying, you can use Gemini because it's free. You can also use All-Mini LM and the small coin models. You can just run these three. Here I just try to put as many models as possible that are used in the industry. But if you want, you can just run 2 or 3. That's enough so that you can go to the next section in the course. So yeah, that is it for this video. I hope that you enjoyed it. In the next one, we are ready to start comparing these models. I'm very excited for that one. I will show you 2 ways to doing it. In the first one, I will show you how to do it manually. And in the video after, I will show you how to do the same thing with a library and add statistical testing. See you in the next video. In this video, we will finally benchmark the embedding models. We have collected everything. We have converted the text chunks and questions to dense vectors. And now all we need to do is to use few metrics to assess the performance of each model. You are going to compare the performance of the models in 2 different ways. First, we are going to do this manually. I will try to explain to you the metrics that we use to compare retrieval models or embedding models in this case. I'll show you the equations. I'll try to explain them to you. And after that, we are going to move to a library called ranx. This library will allow us to basically apply those metrics very quickly without writing a lot of code. And it also has something that is very interesting, which is statistical testing. And we really need this because sometimes we might get 2 models that perform very close to each other, but we don't have a way to say if they are similar or not. And by using statistical testing, we can get something that will tell us if those models are similar or not. Here is an example of what we will get in the end of this video. As you can see, we have the 7 models that I have used in the previous step. We have closed models and open source models. We are going to use both of them. And in the other columns, we have the metrics. We have 3 metrics, MRR, recall, and NDCG. And inside each column or inside each cell, we have the scores. And in the end, we'll see the best performing model and the worst performing model in this benchmark that I have created. And I will explain to you everything in this video. So don't worry about the letters that you see inside the cells. You will understand what they mean. You can also compare the models side by side to get a lot of information, like how many times a model wins against another, or how many times they tie, and how many times a model loses. And all this information we get thanks to ranx. And here, for example, you can see that we are comparing the all-mini LM model to, in this case, the smallest Qwen model. After that, against Gemini, the medium Qwen model, etc. And we will keep comparing the models pair by pair. And after that, for example, here you can see that all-mini LM was able to win against the smallest Qwen embedding model 37 times, but it lost 111 times. So it means that the Qwen model is stronger than the all-mini LM model. So this is something that you can also use in order to compare the models without looking at the scores. Here we have the p-value, which is very important, and we get this thanks to the statistical tests that ranx performs for us. We will talk about this in the upcoming slides. Here I have used just 3 metrics, MRR, recall, and NDCG, but there are a lot of metrics that you can use. So I'll show you all of them and a list that will explain them to you and that will show you how to compute them. We are going to rely on statistical testing to analyze the difference in performance between 2 models. This is a really handy tool that we can use in order to basically say with confidence if a model is better than another or if they are close in performance. Here is the updated pipeline. In the previous step, we were here. We generated the dense vectors for the text chunks and the questions. And now in the evaluation step, we take those as input and output a ranking of the models. So for example, in our case, as you saw in the table, we have 7 models, and in the end, we will have a ranking that will rank those models. So yeah, this is what I'm seeing in these bullet points. The dense vectors are used in the evaluation step, and the output will be a rich comparison between the models. I will show you how to generate those 2 tables, and just by analyzing them, it will allow you to choose if you want to move to a new model or not. Now let's talk about the metrics. We use them in order to compare the performance of embedding models, and there are plenty of metrics that we can use. You have precision, R precision, recall, bpref, F1, etc. So the list is big. I haven't showed you all the metrics, but if you are interested, you can click on this link in order to see all the metrics that you can use. You'll also find how to calculate them and how to use them in ranx. In this course, I will use just these 3, MRR, NDCG at K, and recall at K. And I will explain to you what at K means in the upcoming slide. Let's start with the mean reciprocal rank. This metric is used to measure how quickly the first relevant result appears in the ranked list. Let me show you the equation because it will explain to you how that works. Here is the equation. You can see that MRR is equal to 1 over rank. And in this case, rank is the position of the first relevant document. When I say first relevant document, I mean the correct document. If I take a question, I know that there is only one document or one text chunk that answers that question. And if that document appears at the first position, then rank is going to be equal to 1. And MRR is going to be equal to 1, which is the highest value. If that document appeared, let's say, at the 5th position, then MRR is going to be equal to 1 over 5, and the score is going to be very low. So this is what I mean by measures how quickly the first relevant result appears in the ranked list. Let's see an example to demonstrate this. Consider that you have 3 text chunks where one of them answers the question, and that chunk is marked by this star. Here I have 3 chunks and a question, and chunk 2 answers the question. The first step, so follow this pipeline with me. The first step you do is take all of these, give them to the embedding model, and as the output, you will get 4 dense vectors. Now we will take the question and calculate the distance or a similarity score between it and all the other text chunks. Here I chose to calculate the distance, but you can do the same thing if you want to use a similarity score. If you want to use distances, you can use, for example, the Euclidean distance or the Manhattan distance or the other distances. There are plenty of them. Or if you decide to use similarity functions, you can use, for example, the cosine similarity function, or you can use the dot product. You have plenty of similarity functions that you can use. So after calculating the distance between the question and the other text chunks, you'll get 3 values. And here, if you decide to use distances, you will sort the chunks in an ascending order. Here, for example, 0.13 will be first, after that 0.23 and 0.69. But if you decide to use similarity functions, you will order the chunks in a descending order. Okay, so in that case, 0.69 will be first, then 0.23 and 0.13. But since I use distances, I ordered them in a ascending order. And as you can see, chunk 2 appeared last. So if I take the formula, and rank in this case is equal to 3 because the correct document appeared in the last position, and that gives me 1/3, which is equal to 0.33, which is low. A good embedding model should put this chunk in the first position, and in that case MRR will be equal to 1. Now let's move to recall at k. This metric indicates whether the correct document appears within the top k results. For datasets with one relevant document like ours, the equation is the following. So recall at k is equal to r divided by capital R. Small r is equal to 1 if the relevant document is in the top k results, otherwise it is set to 0. And capital R is equal to 1 because in our case we have one document that answers the question. But the formula that you see here is in the general case, and yeah, let's apply it to that same example. The recall score here is good because as we have seen, we have just one document that answers the question, so capital R is equal to 1. And here, because this document appeared in the top 3 results, small r is equal to 1. And 1 divided by 1 is equal to 1. Let's say that we have retrieved 3 documents, but chunk 2 was in the 4th position. In that case, small r is going to be equal to 0, and 0 divided by 1 is equal to 0. As you can see, recall is perfect, but the problem is that chunk 2 appears in the 3rd position. So recall does not care if your document appears in the 1st position, 2nd, or last. And this metric combines the previous 2 together into one metric that we call NDCG. And this one considers the position of the relevant document, unlike the recall at k. Let's see the equation. So the equation looks a bit complex, but let me explain it to you. First, we have 2 terms, DCG, which is discounted cumulative gain, and the ideal DCG. And ideal DCG means the best output that we can get from the embedding model, which means that the correct document should appear in the 1st position. If that's the case, then the ideal DCG will be equal to 1. But the formula that we will apply is this. So here we have 2 terms or 2 cases. If the document is within the top k results, we are going to apply this formula. Otherwise, it is considered equal to 0 because it doesn't appear in the top k results. And to get the NDCG, we take DCG and divide it by the ideal value. And because here in our case, the ideal DCG is equal to 1, NDCG is equal to DCG. This formula that I'm showing you here is valid for our case because we have just one document that answers the question. But if you want to apply this in the general case, make sure to click on that link that I showed you in the previous slide. It will show you the general formula. And like before, rank is the position of the correct document. Now let's apply this to the same example so that you understand how this works. So in our case, k is equal to 3 because we are retrieving just 3 documents. And let's look at chunk 2 because this one is the one that answers the question. Let's apply the formula. So the formula is 1 divided by log base 2 rank plus 1. Rank in this case is equal to 3, and this gives us 0.5. So as you can see, NDCG is smaller than recall and bigger than MRR. So with the mean reciprocal rank, we got 0.33, recall gave us 1, and NDCG is between them. It gave us 0.5. Now let's move to the statistical test, and let me explain to you why we are going to use them. So this is the table that I showed you in the beginning. And here, after applying all those equations, all those metrics to every model, we get something that looks like this. Now, what does this mean? You can see that here, for example, if we look at this cell, we have 0.8075, but then we have these letters, A, C, F, G. This value means that the Qwen3 embedding 0.6 billion model is better than the models that have these letters. So A corresponds to all mini LM, C corresponds to Gemini, F to the text embedding small, and G corresponds to the large text embedding model from OpenAI. And if you look closely, in some cells we don't have these letters. That's because when we performed the statistical test, we realized that this model is not good than the other ones. And and we can see this. If we look at the all-mini LM, it has the smallest MRR score, the smallest recall score, and it's the worst model in this list. But if we look at the Qwen3 embedding 4 billion model, this one is the best model in this test that I performed. If you look at the scores in all metrics, you'll see that the Qwen3 embedding 4 billion has the highest scores. And if you look at the letters, it shows you that it's better than A, B, C, F, and G, but it's not better than the Qwen3 embedding 8 billion model, because when we performed the tests, we saw that they are similar to each other because there isn't a big difference between these two models. And in order to get this insight, we need to perform those statistical tests. Ranx allows us to do that. And also, we get something interesting. Here, you see that the performance of the Qwen3 model is not due to chance because it is validated statistically. Because sometimes you might get lucky, or you can select the data in a way that you show that a model performs better than another. But if you enlarge the dataset, you will not get lucky, and the model that is general will perform better than a poor model. And with statistical testing, we can prove that, and we can get this information very easily. And this is what I explain here. When you benchmark models, if you get a good score in a metric, that doesn't mean that this model is good. This model might have performed better than the other ones because it's got lucky, or because there is random noise in the data, or because you have selected the data in a way that shows that this model is better than the other ones. With statistical tests, we can determine if the performance difference between two models is real, which means that, yes, this model on paper is better than the other one. It's not due to chance or something else, or because you chose the data in a way that shows that this model is better. And these tests work by challenging something that we call the null hypothesis. We are going to dive a bit deeper in statistics, but the null hypothesis is something like this. Let's read it. So the null hypothesis in this case is the following. The two models are identical, and any difference in their mean scores is just due to random chance. Okay, so this is the null hypothesis. After that, we start running the tests. The output of the test is a probability that we call p-value. And this is the probability of seeing your results if the null hypothesis were true. And here is how it works. So basically, you set a threshold. Generally, we set it to 5%, but you can go lower if you want or higher. You get the p-value. If this probability is smaller than 5%, we are going to reject the null hypothesis. And we are going to say with confidence that model A is better than model B, or model B is better than model A. But if the p-value is greater than the threshold, in this case, it's complicated. So we fail to reject the null hypothesis because we don't have enough evidence. So we are unsure if the model A is better than model B or model B is better than model A. In this case, we don't have enough evidence, so we need to collect more data. And if this holds, then in the end, we say that the two models are basically similar in performance. With ranx, we have access to 3 statistical tests: features randomization test, the students paired t-test, and Tukey's HST test. Don't worry about these. If you want, you can search for these tests online. You can learn more about them if you want, but it's very simple to use these tests within the ranx library. And now let's try to benchmark 2 models. So let's say that model A was introduced, let's say in 2024, and this is our baseline. And we saw that a new model appeared in 2025. Let's call this the new model. We want to know if we should migrate to use model B. How do we do this? We are going to create a dataset and we are going to benchmark the 2 models. We are going to test them on 5 queries using the NDCG metric. Here is a table that shows the score. So here we have the scores per model, and after that we calculate the mean scores. So here we can see that model B performed better than model A. But the question, is this difference significantly better, or did model B just got lucky in this test? Again, we are going to put the null hypothesis, and it says that there is no real difference between the 2 models. And the difference that we are seeing in the table is due to random choice, or random chance, sorry. So our goal is to see if we have enough evidence to reject this claim. Okay, let's start with the paired t-test. This one looks at the differences for each query. So let's do that. We have the 2 initial columns, and now we are going to add another column that will calculate the difference between the scores of these models. So here 0.6 minus 0.5 gives us 0.1, and we will apply the same operation to the other queries. Finally, we get a mean score that is equal to 0.06. The paired t-test checks if the mean of these differences is significantly different from 0. In the end, we get a p-value, and again, we compare it to a threshold. If it is smaller than the threshold, we reject the null hypothesis, and we say with confidence that this new model that appeared in 2025 is better than the model that was introduced in 2024. In the other case, we reject that null hypothesis, and we say that we don't have enough evidence, so we are unsure if this new model is better or not. Randomization test is a bit different. Let's see how it works. So this one, it simulates the random chance of the null hypothesis, because in the null hypothesis, we said that this difference is due to random chance. This test will try to simulate that. Let's see how that simulation is done. So initially we have a difference equal to 0.06. Now what we are going to do, we are going to shuffle the scores. So here, let's look at Q2 and Q4. So here initially model A scored 0.4 and model B scored 0.3. We are going to shuffle those. We are going to flip them. So model B will get the score from model A, and model A will get the score from model B. And we will do that for Q4. And then we will get another difference. And in this case, it's equal to 0.02. So this is the new difference. Now we are going to, or the test is going to apply this shuffling thousands of times to see the differences that we are going to get by chance. And in the end, we are going to count how many shuffles resulted in a difference of that initial value or more. So if we get, let's consider that we got 850 out of 10,000. To get the p-value, we calculate those differences that are higher than the original one, and we divide that by the number of shuffles that we performed. Something that ranx provides is the ability to see the wins, ties, and losses. And now, since you know a little bit about p-value, let's look at some examples. Let's look at the first row. We have all mini LM against the smallest quantity embedding model. Notice how p-value is equal to 0. And when a model is dominating, p-value is always very low. And how do you know that? Let's look at the losses and number of wins. So all mini LM was able to win 37 times. And here, winning means it got the highest score in certain questions. But Quentry was able to beat all mini LM in 111 questions, which is, the difference is very big. And they tied in 229 questions. So because Quentry is beating the all mini LM in a lot of questions, it's dominating. So the test confirms that, and it gave us a small p-value. In ranx, you can set the threshold. And if we compare this to 5%, it's low, so we reject the null hypothesis. But in other cases, you can see that here the p-value is very large. When you see this, it means that the models are similar in performance. Let's take the Quen models, because I talked about them in when I was explaining the values inside the cells. And I mentioned that the 4 billion and 8 billion versions are similar in performance. So let's look at this example. Let's look at the second one because it has the highest p-value. So in recall at 1, both models tied in 352 questions. Quen, the 4 billion, was able to win in 14 questions, and it lost in 11 questions. So you can see that there isn't a big difference between the number of wins and losses. This is why the p-value is high. But let's look at this one. So here you have 9 and here you have 2. In this case, recall at 5, the 4 billion model performed better, and the p-value is not lower than the threshold. But yeah, if you look at all of them, you see that both models are similar in performance. So that is it. I hope that you enjoyed this part. I know that there is a lot of information in this step, but I tried to show you everything so that you understand what we are going to do in the notebook. And you will see that the notebook is very simple. You will understand everything if you have followed the first part of this video. So now let's stop talking about theory and let's start coding. Before I show you the notebook, if you haven't cloned the repository, make sure to do that and try to run the notebook alongside me so that you can understand things, because just watching a course will not benefit you much. You will find the link to the repository in the video description. Open the codebase inside your preferred IDE and open these two notebooks, 5.1 and 5.2. I mentioned in the slides that I will show you how to do this manually, and then we will move to ranx. The dataset that I am using here is the one that we generated in the previous video, and I have mentioned because the size of this dataset is big, I was not able to push it to GitHub, but I will put it in Hugging Face and maybe Kaggle too, and so that you can download it. So after you download this, make sure to put it inside the embeddings folder. Let me show you. If I scroll up, I have the data folder. Inside it, I have the embeddings folder, and here is the file that we are working with. So let me load it and let's look at the statistics. So we have 43 text chunks and 377 questions. The first thing that we are going to do is talk about the evaluation metrics. We have 3: MRR, recall, and NDCG. If you want to read more about the metrics, click on this link. It's the same link that I showed you in the slides. And as you can see, we have a lot of metrics. and you can click on all of them. Let me show you. I can click on DCG, and here is the general formula if you want to apply it. So let's start with the mean reciprocal rank. Here is the formula. It's 1 over rank, and here is how to do that in Python. If for some reason rank is not defined, we are going to return 0. Otherwise, we are going to write the formula. So this one is simple. Now let's move to recall at k. The general formula looks like this, but since we have just one document that answers the question, we can simplify it by setting capital R to 1. And this gives us something very simple. So recall at k is going to be equal to R. We return 1 if rank is within the top k results, otherwise it's 0. Finally, we move to the NDCG metric. It looks a bit scary, but we are going to simplify it because in our dataset, we have just one document that answers the question. So NDCG at k becomes DCG at k, and here is the formula. If the rank is within the top k results, we write this formula. Here it is, 1 divided by log 2 rank plus 1. Otherwise, if the document is outside the top k results, we return 0. Great. So now let me define all these methods, and now let's continue. So first of all, let's get the list of embedding models. I'm going to get them from one of the chunks that I have in the dataset. And as you can see, we have 7 models. Now we are going to create a mapping from each question to its correct chunk. This is why we created that chunk ID in the beginning, so that we can link the question, the question to the answer. And the answer to that question is the chunk. The first 4 questions can be answered by the first text chunk. And here how many? 1, 2, 3, 4, 5, 6, 7, 8. And the next 8 questions can be answered by the first chunk. So here we are just linking each question to the document that answers it. Let's continue. And here we just extract the IDs from the chunks list. They are going to be in order. And now in this cell, we are going to create NumPy arrays because we are going to calculate similarity between the dense vectors. And by converting them to NumPy arrays, we can make these calculations efficiently. So let me show you how that looks like. So I can take the chunk embeddings, let me put it here, and after that, let's look at it. So this is a dictionary where we store the dense vectors per model. So now let me take, for example, this model, and let me look at what we have inside. So let's do this, and this is the result. And this is an array. Let's look at the shape. We have 43 text chunks, and each vector contains 1024 values. So this is the dimension of the embedding vector. And we can do the same thing for the questions. We saw that we have 377 questions, and this is what we get. Great, so let's keep going. So I've done this for Gemini also, and Gemini has 3072 values per dense vector, and the 8 billion Qwen tree model can go up to 4000 values. Now let's run the manual benchmark. Here I'm explaining how the loop works. First of all, for each model, we calculate the cosine similarity. As I mentioned in the slides, you can either use similarity functions or calculate distances. So here I went with using similarity scores, and I'm going to use the cosine similarity method. And we are going to do this between every question and all chunks. And after that, for each question, we are going to rank those chunks by similarity and find the position of the correct chunk. After that, we compute the 4 metrics like how I showed you in the slides for each question, and then we are going to average the scores for each metric. Let's see this in action in code. So here we start by defining this method that I called getRank, and it's going to give us the rank of the correct chunk. So here we have the list of the rank chunk IDs, and we have the ID for the correct chunk. We get the index and we add 1 so that we start from 1. If for some reason we don't find it, we are going to return none. Okay, but let's start. So for every model, we are going to get the question embeddings, the chunk embeddings, and we are going to use the cosine similarity function from scikit-learn. And because it accepts NumPy arrays, it's simple. So it's going to perform that calculation over these two matrices, and it's going to give us a similarity matrix. So inside this similarity matrix, we have the similarity score between the questions and the corresponding text chunks. Let me show you how this works. So I can take this, put it here. Let me define GQDM also, and the cosine similarity. I will also add a break. I always like to do this because you need to try to understand each iteration individually before running the full for loop. And yeah, let's just run this. So it ran, everything worked. And now let's start looking at the shapes. So if I take all question embeddings for that specific model, we get the same thing. And here we start with the all mini LM. I know that's because the shape or the dimension of the dense vector is small. And we can look also at the chunks. It should be, let's not look at the similarity matrix for now, but the chunk embedding should be 43 because we have 43 text chunks. Now we have also the similarity matrix. Let's look at it. So it's going to be 377 by 43. And this calculates the similarity score between every chunk and question. So we have everything here. And let me show you this. So we can print it. You can see that the values are going to be between -1 and 1 because we are using the cosine similarity matrix. And now we loop over the questions. Let me take this whole block and put it here. Okay, and let's add a break. Okay, so we get rank, and here let's try to print all of these. So let's take this, let's delete everything, and let's replace that by print. We need to define the getRank method, so let's put it here. We have our break statement. Let's run this. Okay, so we were able to calculate the metrics, but how did that work? So first of all, we get one question. We need to know the document that answers it. So we need to use the ground truth mapping. And let's look at ground truth. So ground truth is this dictionary that we created to map from each question to its correct chunk. For example, if I am looking at the first question, the ID of the first chunk is 0. So this is what I am getting here. And let's verify that. If I look at the correct chunk ID, it's equal to 0 because I am looking at the first question. Let's keep going. And after that, I'm going to get the similarity matrix and look at the same index. So let's look at that. So scores for this question. Here, if I look at the shape, we will have 43. Why? Because we have 43 text chunks. So this is the similarity score between that question and the other documents. If you remember the pipeline, let me show you the pipeline. Here it is. So we were able to compute the similarity scores. Here they are, all of them. Now we need to sort. Let's see. As you can see, we are going to sort them. Let's look at the sorted scores. Let's put them here. And yeah, as you can see, the scores are sorted. So the first one has 0.27, 26, 23, etc. And after that, you get the chunk ID alongside that, the score. Now let's look at chunk scores. And here we are using this list that contains the IDs for the chunks, and we are zipping it with the scores. Let's see what this does. So chunk scores is going to be like this. So as you can see, each document or each text chunk has its own similarity score with the question. And now we use the sorted method to sort that. We want to sort it by the score, not by the chunk ID. That's why we are selecting the second item in that tuple. After that, we get the chunk IDs. Let's look at them. Here they are. And we use the getRank method to give us the rank of the correct document. And we know that the correct document is 0. Here it is. It's 0. And if we count 1, 2, 3, 4, 5, 12. So this gives us 12. Let's look at rank and let's validate this. Yes, so it gives us 12. And now we apply the formulas. So MRR is 1 divided by rank. Let's validate that. So I can take 1 divided by rank. It gave us 0.08. Since the rank is very big, it's 12, it's not appearing in the top K result. That's why we got 0, 0, and 0. So yeah, it's working. And now I can remove these because I explained to you how those work. And I can also remove this. Now let's go back. Now we're on this in a loop. So we are here. And in the end, once we append all these results, we are going to calculate the mean. Because we have how many questions here? We have 377 questions. And in the end, we just want to get one score. That's why we calculate the mean for each metric and put that in a dictionary. Let's run this. It's finished. And yeah, we can look at these scores. So here we have the metrics. We can calculate the max and minimum score for all of them and print them here. So the maximum, let's see. So the maximum MRR is 0.83 and the minimum MRR is 0.71. We are calculating this so that we can highlight the worst and best model. And here we are using the rich library to be able to generate a table that looks nice in the output of the notebook. I have also created this cell that will create another column that will average the metrics and then sort the models based on the average. We can clearly see that the All-Mini LM is the worst model and the medium and large Qwen tree embedding models are the best. You can see that here we don't have those comparisons because we are doing this manually, and here I am not doing the statistical testing. I want to show you this in the second notebook. Now we can close this notebook and go to the second one. We do the same thing. First, we load the dataset. We have the correct number of chunks and questions. And after that, we start working with the ranx library. Here we start with something they call query relevance judgments. This is the same mapping that we have done before. Let me run this cell because it takes a few seconds to complete. So it took 2 seconds. So we give this method the questions, and here we create a dictionary. Basically, this will map the question. So here we have the query ID. Let's look at it. So let me show you. This is how you should try to run these notebooks. Try to take something from within a method and try to run it manually. And this is why in my courses, I try to create notebooks instead of Python scripts, because with notebooks, you can dive deeper and try to understand everything by running them in cells. If I take this, let me show you this dictionary. And this is the mapping. This is exactly what we have done before. You can see that the first 4 questions, here we have the first 4 questions, and we gave them 1. And here, for example, the second, I think here we have 8 questions. They all map to the second chunk, etc. So this is the content of QRL's dictionary, and you can click here if you want to read more about this class. Here it is, and they show you how to instantiate that. And here, let me zoom in. Here they are showing an example where 2 documents can answer a question. In our case, we have just 1 question, but this is the general case. You can have more than 1 document that answers a single question. And you can see that sometimes that document can answer 2 questions. For example, the second document appears in the first question and in the second question. Now let's go back to the notebook. We created the QRLs. Now we create the runs. Again, click here because that will take you to the documentation. And here they show you how to create a run. And here you can read more about this. And here is how we do this. And we are going to have multiple runs, 1 per model. Let's run this. And as you can see, here we have the models to benchmark. This is a list that contains the model names. Here they are. And now for each model, we are going to create a run. And that run will take chunks, questions, and model name. Okay, now let's go inside the create run from data and let's look at it. So first of all, we create an empty dictionary. We retrieve the chunk and question embeddings from that model. So here we have our chunks and questions. We calculate the similarity scores. We get the chunk IDs from the chunks list. And now we are going to loop over the similarity scores. And for each chunk ID, we are going to put the score related to it. So here inside chunk scores, we are going to have, for example, the first chunk will have a score, the second chunk will have another score, etc. And we put that inside this run dictionary, and it should have the same query key that we used here when we created the Q roles. You can see that the Q roles, this is the key. It has this prefix Q underscore, and we are using the same thing. But here we are putting the chunk scores. I know that it's very hard to understand this just by reading the code, but again, we will do the same thing. We are going to copy the code. Let's put it here, but we need a model name. So let's take the first one from this list. Or actually, let's see. Let's take 0, 1, 2, 3, 4. Let's take this one. And let's go through this step by step. So let's take the first part. Here we have the chunk embeddings. Let's look at the shape, chunk embeddings dot shape, and question embeddings and similarity scores. Okay, so we have 43 text chunks. The size of the embedding vector is 4096 because we are using one of the big embedding models. Yeah, we are using the 8 billion quantity model. We have 377 questions, and the similarity score is correct. Great. Now let's continue and let's look at this. And here, since we have a for loop, let's add a break statement and let's look at this. We are interested in chunk scores. Okay, so let's run this, take chunk scores, and let's look at this. You can see that here we have a mapping between the chunk ID and the scores. So here the first chunk has this score, 51, the second one, 0.44, etc. So this is the content of chunk stores, and the run dictionary will be like this. So you have that specific prefix Q underscore, and because this is the first question, yeah, because here when we use enumerate, it's going to loop, let me show you the shape. It's going to loop over the questions, not the text chunks. So this loop will run from 0 up to 376. Let me remove the break and show you that. So if I print the keys, you'll see that the last value is 376. And this is the format that ranx expects you to use when creating the Q roles and runs. And based on these two, ranx will try to calculate the metrics and perform the statistical testing. So far there is no calculation. We are just preparing the data for ranx. We have the Q roles and we have the runs. Now here's how it works. You can see that we use this compare method. We give it the Q roles and runs and the metrics that we want to take into consideration. So we have MRR, recall at 1, recall at 5, IndCG at 5, and I could add more if I wanted to. If you want to go back to the documentation, click here, go down until you find metrics, and here you can just take these values. So if you want to add hits, take the alias and put it there. If you want to add F1, take it from here and add it to this list. If you don't know which metric supports the @k notation, you can come here and look at the @k column. If you see yes, that means that you can take the alias and add a number like we did here. So if I go to recall, you can see that we have yes, so which means that I can type recall at k. And after that, you set the maximum threshold. Here it's set to 5%. And the statistical test. Here I set it to Fisher, but if you hover over this and scroll a little bit down, you'll see that you can set other statistical tests. Use Fisher if you want to use the Fisher's randomization test. Set it to student if you want to use the paired student t-test. And finally, you have Tukey for the Tukey HACD test. If I run this, it took 1.4 seconds and it performed the same thing that we performed in the other notebook. meaning it calculated the metrics, and on top of that, it performed this statistical test. So let's display the results. But first, we need to assign each model a letter. So all mini LM will get A, etc. And now we can print this. Up to this point, I'm just trying to make the tables look nice. Here we are calculating the maximum and minimum scores. And finally, we reach this cell where we print the data. And I think I also have, I have done the same thing. So I calculate the average and rank the models accordingly. As you can see, we have those letters that I showed you in the slides, and it makes sense that we don't have letters here because this is the worst model and all of them are better than the A model. And here the 4 billion model is better than all of them. Same thing with the 8 billion model. Let's try to analyze what we have here in the cells. You can see that I mentioned that NDCG is a combination of MRR and recall. Let's see why. So MRR for the Quen model is 0.83, recall is 0.96, but NDCG is 0.86. So it falls in between MRR and recall at 5. Because here recall doesn't care about the position of the document, but NDCG does. So in order to print the win, tie, and loss table, we have this win, tie, loss dictionary from that report. Yeah, let's look at it here. So we have the report and we have the win, tie, loss attribute, and it contains everything. Here it's compared the all mini LM with the small Quen model, and it gives you the wins, ties, and losses per metric. And here we can see that wins and losses are shown for the first model. So this means that all mini LM won 37 times and it lost 111 times, etc. You get the same thing for recall and NDCG. So I basically took what I have here in order to generate the second table, which I create here in this cell. The table is big because here we compare all the models against each other. Here, all mini LM loses every single time because it's the worst model. But with the 4 billion and 8 billion model, they are similar to each other, but still the 4 billion beats the 8 billion model. And how do we know this? We just look at the p-value. Here, if we go back to the all mini LM, the performance of this model is poor. That's why the p-value is small, because this model is way better than the all mini LM. But once we go a bit down and look at the 4 billion model and 8 billion model, we saw that the scores are close to each other. This is why the p-value is larger than the 5% that we set as a threshold. Just by looking at this, we can't reject the null hypothesis. And this is why, if I go back to the first table, we saw that we don't have we don't have an E letter here with 4 billion, because it means that the test that we performed showed that the 4 billion model is not better significantly than the 8 billion model. They are both performing well, and we can use either one of them. So if, for example, the 4 billion is cheaper than the 8 billion, it's better to use the 4 billion model. But at this stage, we cannot conclude. Why? Because here I am just using one document. I am planning in the upcoming videos to show you how these models are going to evolve once I keep increasing the size of the dataset and keep adding documents from different domains. Behind the scenes, I'll try to increase the number of documents, and we'll see if the 8 billion model will hold or the 4 billion model. And what I like about doing this manually is that we validate the performance of the models. If you remember, I've shared with you the MTab leaderboard 2 times in the slides. And here, if we look at this leaderboard, we can see that the Quen 8 billion model is better than the 4 billion model. And Gemini embedding sets in between. We got something similar, but in our case, the 4 billion was better than the 8 billion model. This is a big data set. It contains a lot of tasks. That's why here the 8 billion model was able to generalize a lot, and it's got a better mean score. So if we come here, the mean score here is 70%, and with the 4 billion model is 69%. You can see that even here in the MTab leaderboard, the performance of these models is almost similar. But here in this case, the 8 billion model was able to beat the 4 billion. If we look back, we see that the 0.6 billion model appears after the 4 billion and the 8 billion models. We need to make the datasets big because sometimes you might have models that are good in English, and other models might be good just in French. Some models are going to work very well on multiple languages. We will see these things in the upcoming videos. We are going to translate the dataset. We are going to add more documents, and these scores are going to converge into one stable configuration in the end. This is the last thing that we do in this notebook, and I went very quickly through these cells that create the tables, because here we are just displaying the data. There is nothing very important here. What's important is what I showed you in the beginning of the notebook, where we talked about the metrics and the statistical tests. Here, increase this to 10 and do the same thing here. I can quickly generate another table and look at the data. So let's do that quickly. And yeah, as you can see, we have another table and the metrics have changed. Now we have recall at 10. Look at the recall. Now we are getting almost perfect scores, because when you increase the recall, the task becomes very simple for the embedded models. So the best thing to do is to keep the recall small, because here, recall at 1, the scores are low. But if you increase the recall, then this becomes very easy. And the recall and the value of k depends on the size of your dataset. If you are working with hundreds of thousands of documents or text chunks, in that case, you can set k to something around 100 or 200. But if you are working with 1,000 or 2,000 documents, setting it to 100 will make it very easy for the embedded models. But yeah, I'm just showing you here that you can change this easily if you want to. So that is it for this video. In the next one, I will try to work hard by generating more data. And after adding more documents, after creating more questions, I will show you the progression. So currently I have almost 400 questions. My plan is to generate another 400, do the benchmark, and then generate another 400 questions, do the benchmark, and after generating maybe 1200 questions, I'll come back to you with another video where we show the progression. So I will show you how the scores were when we had just 400 questions, then how they changed when we had 800 questions, and finally when the dataset is big enough where we will have maybe 1200 questions or more. When we reach that, we will have a large data set that will give us a real idea of how these models perform. And until then, have a wonderful day. See you in the next video. In this video, we are going to expand the dataset by adding more domains and languages. You will learn how to find multilingual embedding models on Hugging Face. We will also run different benchmarks to see if the performance stays consistent when we change the language of the questions or the text chunks. In this step, we are going to expand the dataset. We are going to add more domains and languages to see if the models can generalize. The goal is simple. We want to test if these models actually understand meaning across languages, or if they just got lucky on the small English test that we used in the previous video. This is the table that I showed you in the previous step. We saw that the Qwen3 embedding 4 billion model performed better than the other models, and in this video we want to see if this model can keep its top spot when we scale up the data. Here is how we are going to do this. First, I added new PDF documents to the documents folder. Then I ran the notebooks again to generate questions and text chunks from these documents. Finally, I generated the embeddings and saved them as JSON files. For the multilingual part, if you don't need other languages, you can skip this. But if you do, you can translate the text manually or use an LLM to get a good result. I have created 3 notebooks for that. The first one uses Gemini, the second one uses OpenAI, and the last one will use a new open source model that is called Aya. This one was trained on a lot of languages. That's why I included it here. Once the text is translated, you generate the embeddings for the new language and save the JSON files, like I'm showing you here. And these files are available on Hugging Face. You'll find the link in the video description, or if you check the GitHub repository, you'll find a link that will take you to the Hugging Face repository where you can download these datasets. When selecting an embedding model, make sure that it was trained on the language you are targeting. If you pick a model randomly, you might download a model that doesn't support your target language. The results will be very, very bad. Here, for example, I am showing you the all-mini LM model. And as you can see, the scores are almost 0. So here we have MRR is 0.07. And if I average all these scores, I get 0.06. And the all-mini LM was not trained on the Arabic language. And here I have benchmarked it on that language, and it performed poorly. That's because this model was not trained on that language. So this is why I'm saying that it is very important to read or to find if the model that you are looking at is able to work with the language that you are targeting. For open source models, go to Hugging Face. In the Tasks tab, select Sentence Similarity. After that, click on the Languages tab and select the languages you need. The search result will show you the models that support the languages that you selected. You can also find how many languages a model was trained on by reading the model card. In this case, we can see that this model was trained on 70 languages. For closed source models, check the official documentation or read the release blog posts. Let's test the models on the English dataset. In the previous video, I had almost 400 questions, but now I was able to generate another 400 questions, and here are the results. We can see that Gemini is performing better than the other models. And if we look at the average, we see that the top 3 models all have a score greater than 70%, and the all-mini LM is falling behind. So it is the worst performing model in this list. I have also added another 400 questions. So this is the maximum amount of questions that I generated from those documents. And we see that the Qwen3 Embedding 4B model claimed the first position back. But if we look at the average, we see that the scores are very similar. And this is expected because these models are trained on English. So that's by default, all these models will perform well on the English language. But when we move to other languages, we see that some models are going to start to perform badly because the amount of data that they was trained on is less than English. Now let's see how these models are going to perform on the Arabic dataset. It's the same dataset, I just translated it from English to Arabic. Here are the results. We see that Gemini this time is performing better in both cases. And if we look at the 1200 case, or both of them, we see that the all-mini LM is getting a very low score. This is the score that I showed you in one of the previous slides. And this proves that you need to be careful when choosing a model. And here all-mini LM was not trained on Arabic. We also see that the OpenAI models, they also struggle with Arabic. So the score is not 0 like the all-mini LLM, but it's 50%, which is low. And if we look at, let's go down here, if we look at Gemini, Quentry, Embedding 8B and 4B, they all perform well. So we see that the score is greater than 70%. That's great. This means that both these models are multilingual, which means that they were trained on multiple languages. And we are going to dive deeper into this concept, multilinguality, in one of the upcoming slides. Let's also compare the scores between English and Arabic. Here I took the 1200 questions set, and we see that the rankings are almost similar. We see that all-mini LLM is always last. We have the OpenAI small and large models, and after that, we either get Gemini embedding in the first position or the Qwen 4B model. And if we look at the scores, we see that the scores didn't drop too much, especially the top 3 performers, one of the Qwen models and Gemini, they always get a score higher than 70%. But if we look at the OpenAI models, the performance dropped from 71% to 59%. Now let's talk about multilingual embedding models. This is a fascinating part. I really love this thing about embedding models. And the question here is, how does the model handle 2 languages at once? The model doesn't just match words. It learns the abstract meaning of the text. Let's say I took the word learning in English. If I translate that to Arabic, the vectors that represent these words will land in the exact same spot in the vector space. Look at this chart. The blue dots are English questions and the red dots are Arabic questions. You can see the questions are clustered together based on the topic, not the language. And this is what I am showing you here. Here we have 2 points. They are very close to each other. If you calculate the distance between them, you will get 0.00 something. And here I am showing the question and the translation. So if you can read Arabic, you will understand that these 2 sentences are basically the same. And when using a multilingual model, we see that the embeddings are located at the same position. This is so cool. Training embedding models on different languages makes them learn the meaning of concepts in different languages. The learned space becomes language agnostic. Since we are talking about multilingual embedding models, you can store documents in different languages in the same index. This makes retrieving information simpler because you don't need to manage multiple indices, one for Arabic, another one for English, and another one for French, let's say, if you are targeting these 3 languages. You can put all those documents into one centralized index if you decide to use a multilingual model. However, performance might drop a little bit compared to single language indexes. This is because we will add a little bit of noise when we merge those datasets into a gigantic dataset. And the noise happens because the vector space gets crowded. When you add more languages, the chance of an English query accidentally landing near an unrelated Arabic document increases. And this is called interference. This happens a lot especially if a model is not trained well on certain languages. Those languages might add noise in that embedding space. And here I'm showing you a table where I merged the English and Arabic datasets into one dataset that contains 2,400 questions. And we can see that the average dropped a little bit. Before it was higher than 70%, but now it's around 68%. It's not a big drop, but this proves what I mentioned now. If you decide to merge the datasets, you need to use a powerful multilingual model so that the performance or the accuracy does not drop. But if you don't like the idea of merging documents in different languages in one vector store, we can try something else. We will perform 4 tests with these combinations. In the first one, we will ask questions in English, and the index will have text chunks in English. In the second one, we will keep the text chunks in English, but we will ask the questions in Arabic. The third test is similar to the second one, but the questions are going to be in English and the text chunks are in Arabic. Finally, both the questions and text chunks are going to be in Arabic. Here are the results of those 4 tests. The results are really cool. At first glance, we see that the average score did not drop below 70%. Let's look at the top model in each benchmark. We see that here we have 75%, 72%, 74%, and 73%. This is true only for models that are trained on multiple languages. But again, if we come back to our friend all-mini LM model, we see that yes, it performed okay in the English case, but when we start to include Arabic, this model quickly starts to degrade. Here we get 0.09, 0.08, and 0.06. We also see that the OpenAI models are average. They perform similarly to the smallest Qwen model. For example, here in the English case, they perform well because that's the main language. But when we ask questions in Arabic, we see that the performance drops by a lot. So here it was 71%, now it's 52%. It drops by 20%. That's a lot. And here, as I mentioned, the large model is performing like the smallest Qwen model. And sometimes that model beats both of them, especially in the Arabic case. The stars of the show are Gemini and the Qwen 3 4 billion and 8 billion models. I really love these models, and sometimes you can see that sometimes the 4 billion model performs best, sometimes the Gemini model performs better, and sometimes the 8 billion model performs better. In our course, we are not trying to generate a big benchmark like the MTEB leaderboard that I shared with you multiple times in this course. No, here we are trying to create I would say a representative dataset, a benchmark that is going to be used by you or inside the company where you work, where you are going to collect documents on a specific domain. Let's say that the domain is astronomy, and let's assume that this domain doesn't exist in the MTEB leaderboard or any other benchmark. In this case, you care about this domain and you don't care about other domains like technology, healthcare, or others. Collect as many documents as you can in the astronomy domain, extract the questions and the text chunks. If you can generate 1200 questions, 2300, that will be good. When you create that dataset and benchmark the models, you will get how those models perform on that dataset. And you don't care if Gemini is better at healthcare or other domains. All you care about is the astronomy domain. And this way you will have something specific, something niche that will tell you which model performs well on that specific case. And of course, if you don't care about other languages, you can keep that dataset in the original language. And by creating that dataset, you will be able to test new models on it, because you will create a table like I did here. And after that, when a new model comes, you will use the notebooks that I showed you, quickly benchmark that model and see where it lands in the table. If you see that this new model is better than the rest on that specific domain that you care about, you say, now we have a new model. So you can use it in your applications and see how it performs and see if it actually improves the performance of your applications. This is why I created this course, and this is how to benefit from it. Because yes, the MTEB leaderboard is great. It gives you a holistic view of how these models perform on hundreds of tasks. But sometimes some tasks are not going to be there. So it's your turn to create a dataset on that task to find the models that perform best on that use case that you care about. That's enough for the theory. Now let's go practice. Before showing you the code, here is the GitHub repository that I was talking about. If you scroll down a little bit, you will find this note. When you click on this link, you will be able to find the repository on Hugging Face. And here I have uploaded all those documents that you can download. So if you open the datasets folder, you will find two versions. Here, for example, this file is the English version and the other one is going to be the Arabic version. So just download these one by one by clicking on them here, or download the whole repository. And when you do that, put everything inside the embedding folder. Open the Explorer, open data, create this folder, and put your JSON files here. After you do that, you need to open one of these notebooks. So I have created 3 notebooks for this step. Here we have a way to translate text with Gemini and OpenAI models. These are closed source models. And if you want to use an open source model, I have chosen Aya. This one is a special model. It was developed by Coherent Labs, and this model was trained on multiple languages. And the good thing is that this model is open source. You can see that if you open Hugging Face, you can find that model here. And they have multiple versions, so you can install the small variation 8 billion, and they have the 32 billion. So I'll show you how to use that. But with open source models, you can use any model. Just make sure that it is trained on multiple languages so that you get good translations. Let's start with Gemini. The first thing here, we define the language. I chose to define Arabic, and here we are going to just set up a system prompt. So this step is not complex. The only thing that you need to work on is the system prompt. And here you can see that the system prompt is not that long. We explain the task to the model, and here we are telling it that the role is a world-class translator, and we give it some instructions. We don't want it to add or remove anything from the original text. We want it to stay the same, but to be translated. We need to maintain the original tone and return the translated text without any additional commentary or explanation. So we don't want the model to say, okay, here is the translated text. We just wanted to give us the translated text. And after that, we give it the language that we want to translate into. So let's run this. After that, I create a Pydantic object so that I can extract the text easily. And in this cell, I load the data. So I chose one of the documents that I uploaded, and I'm going to load the text chunks and questions for that specific document. In this case, we have 43 text chunks and 377 questions. And in order to use Gemini, we need to create an instance of the client and start. Here you can see that we are using Gemini 2.5 Pro. And now we have the option to also choose the Gemini 3 Pro because it was released recently. But I'll keep 2.5 Pro because the new Gemini is under stress, so you might get rate limited. So that's why I will keep it as 2.5 Pro. And the logic is the same. So you use the generate content method, you pass your system prompt and the text here comes from the chunks. So here we are going to start by translating the chunks, and after that we will translate the questions. And you will notice that I added 2 variables, max retries and initial delay seconds. I did this because I was getting rate limited when the new Gemini 3 Pro was released, and I wasn't able to run this loop without getting errors. So I added a retry mechanism to keep retrying up to 5 times. And this helped me get over that problem. And this is how it works. So first you put a loop inside the first for loop, and this loop will run max retries times. So in this case, it's going to run 5 times if we get an error. But if everything succeeds, we are going to break out of the loop. And here we have initial delay seconds. So when we get the first error, we are going to wait for 2 seconds. But after the first error, if we get another error, we are going to multiply that delay by 2. So we are going to wait 2 seconds in the first error. After that, we will wait for 4 seconds, 8 seconds, 16, etc. We are doing it like that so that we give the server a chance to maybe recover, to get healthy, so that we don't get errors quickly. So that's the logic here, and as the rest is the same. So and as you can see, this is what I was getting. So the server was always responding by the model is overloaded, please retry. And you can see that here is the first attempt, the second, the third, etc. And the fourth succeeded. But if we didn't have this, the code will stop and we'll have to retry from the beginning. And it takes a lot of time, and I really didn't like how it behaved. So that's why I added this. So let's run this. I will add a break statement here to translate just one chunk. And let's see if this time it's going to work. And yes, it did work. You can see that we didn't get any error, and this inner loop stopped after getting a successful iteration. And here, when I take the translated text and put it back in the dictionary. So now if I take the text chunks list and look at the first element, we should see that it was translated. So if I go and take a look at the first element in the list, you can see that now it's in Arabic. And some text was not translated because that's the name of the company. And yeah, it's the model did a great job, so it kept it in the original text, but the rest was translated to Arabic. So that's working. And we are doing the same thing in the next cell, but instead of looping over the text chunks, we are looping over the questions. And yeah, after that, you see I was getting a lot of errors, but at least the code didn't stop and I was able to translate everything. Finally, we need to save the files, and I decided to save them in the same place. So if I look at the chunks, you'll see that I have the original documents that we worked with before, and this one doesn't have any suffix. So this is the English version, and the version that was translated has a suffix, and this one has the Arabic suffix because that's the language that I targeted. And we have the same thing for the other document. And yes, you can add more languages if you want. Here I just stopped at Arabic, but if you want to add French also or other ones, feel free to change the target language variable here and rerun the notebook, and you will get another file stored here. So this is how you use Gemini. And to use OpenAI, it's the same thing. So you just change the library. Instead of using the Google Generative AI package, you use the OpenAI package. So I'm not going to show that. And with Aya, we have the same thing. So here, because the Aya model is a big model, I decided to use, again, the GGUF format. And here I used the bigger version. So I used the 32 billion model. And here I linked to a repository where you can find the GGUF format. And feel free to download the one that works best on your machine. I always go with Q4 because I don't have a lot of resources. But if you have more, we can go up to Q8. Or if you don't have a lot of resources, you can go down to Q2, or in this case, we don't have Q1, but you can use Q2 if you want. Okay, so here is the Aya model. And as I said, it's not required to use the Aya model. You can use, for example, Gemma or Qwen. All of those models are perfect. They are trained on multiple languages, so you can use them. But here I'm trying to show you that in the open source ecosystem, we have a lot of options to play with. And that's a great thing. Here is the command that you should use to run the Aya model. Because this one is big, I wasn't able to upload a lot of layers to the GPU, so I was able to upload just 5. This is not good because the model will run very slowly on my machine. But if you can, make sure to increase the value in the number of GPU layers parameter so that you can get faster responses. And yeah, let me show you again how to do this. You copy the command, you open the terminal, and you run it. And if you see this message, it means that the model loaded successfully and we can use it. Now go back to the notebook and run the following cells. So the system prompt is the same as the one that I defined in the Gemini notebook. Here we load the data, and here is the method that we will use to translate the text. First, we specify the endpoint and make sure that the port is the same one as the port that you specified in the command, so that you don't get any error. And inside we have the same thing that we worked with before. So you have a list of messages, you put the system prompt in the first item, and after that you add the user message, and in that role you put the text that you want to translate. And after that you make a post request to that endpoint, and if everything went well, you decode that response and you should get the content, which hopefully will contain the translated text. Now run this cell, and here I will add a break. And you see that here I didn't add that retry mechanism because the model is running locally and we will not hit any rate limits. We don't need it in this case. So let's run it, and let's go back to the terminal. You see that the number of tokens is 1335. That's a lot. Actually, let me stop this because it's going to take some time, and let me do it. Okay, so these are the text chunks. Let me do it in the questions because the questions are not big, and hopefully they should be. Yeah, you see that here we have just 148 tokens, so we should be able to translate them quickly. While waiting, I want to show you the output. And yeah, for those that can read Arabic, you can read this text and you will see that it's perfect. I really like this model. It does give good translations, and I like that it keeps terms like Asus computer, things like that. So the model does not tries to translate them to Arabic, and that's a good thing. But if you don't like that, you can take the text and modify it manually to change these terms. Okay, here I have a bug. So here response it's just a string, so it shouldn't be response.text. But as you can see, the text was translated to Arabic. That's good. And here, I need to fix this. So I need to remove .text so that we don't get that error. Good. And after that, you save the translated data. After translating your documents, you can use this notebook or the other two that are meant to be used for benchmarking. And this one, the third one that I added for this video, will perform those 4 benchmarks that I mentioned. And this notebook uses the same code that we have in the second notebook. So I try to put everything inside one cell just to make things quick. So here in the first part, we load the data. You'll see that in the Arabic dataset, we have 120 chunks and 1200 questions. And we get the same number in the English version because they are the same. And here we have the benchmarks section. And in this cell, I have merged all the codes that will perform the benchmark, print the tables, and everything, because this is going to be used by all the 4 benchmarks that we are going to perform. Just to show you, we have a function that creates the Q roles, a function that will create the runs, and these are things that are used by the ranx library. The print benchmark report is a function that will print the tables. It's going to use the rich library to give us a nice table. And you can see that the code that we need to run to perform the benchmark is very small. For example, here in the first test where we have questions and chunks in English, you see that this is the code. And when you run it, you'll be able to see the table. And this is exactly the table that I showed you in the slides. And let me show you how that works. So first, we need to create the runs for each model. Here, the models to benchmark are always those 7 models. Here they are. So we create a run for each model and we append them to the runs English list. After that, we create the Q roles and we pass both of them to the compare method. And after that, you can see that here we are using statistical testing. We provide the maximum probability and the metrics that we want to see in the table. And the print benchmark report will take the output from the compare method and it will give us a nice table. This is the first test, and you see that most models perform better on this one because we have the English language. But in the second test, we change just the questions. So runs will not change, but here when we create the Q rules, we will pass the Arabic questions. We will not pass the English questions. So when we do this, we'll get a different result. You see that the all-mini LM doesn't perform well on this benchmark, but the rest are doing great, especially the Gemini embedding model. If we swap the English and Arabic in the third test, we get a similar result. And yeah, you see that the all-mini LM doesn't perform well, but those three are always on top, and the average score is always higher than 70%. And in this specific case, we change the runs. You see that here we provide the Arabic chunks. We don't use the English chunks, but since the questions are in English, we pass the English questions to the create Q rules method, and the rest stays the same. And for the final test, we pass all the Arabic variables. So we pass the Arabic chunks and Arabic questions to the create run and Q rules methods. And finally, we get this result. And you see that in this case, the OpenAI models are suffering. The performance is okay. The all-mini LM is not good at all, but Gemini, Qwen 8b and Qwen 4b models are doing really great on these two languages. So that's it for this video. See you in the next one. Congratulations on finishing this course. We have covered a lot of ground together. You started by understanding what embedding models are and why we cannot always rely on public leaderboards like MTab. You learned that the best model on a public leaderboard might not be the best model for your specific private data. We went through the entire pipeline. We created a golden dataset by generating question-answer pairs from our own documents. We ran both open source and proprietary models, and we evaluated them using metrics like MRR, recall, and NDCG. You learned how to use statistical tests with the ranx library. This ensures that when you say one model is better than another, you know it is because of actual performance and not just random luck. We also explored the multilingual capabilities of these models. We saw how vector spaces can be language agnostic, allowing us to retrieve English answers using Arabic questions. But we also saw the trade-off. When we add too many languages to one index, this can introduce noise and interference. Finally, we saw that the quality of your evaluation depends entirely on the quality of these question-answer pairs that we generated during the course. The most important takeaway from this course is trust your data. Don't just pick the model. Don't just pick the most popular model. Benchmark it, test it, and prove that it works for your specific use case. I hope you found this course helpful. You can find all the source code and the notebooks in the GitHub repository linked in the description. Feel free to use them as a template for your own projects. Thank you for watching and happy coding!